Questo è risultato.
Ai, muito obrigada. Então, sim, sempre.
É a Maria que está sempre a desconectar. Olha, eu vou passar para. Posso passar para a porta de baixo? Eu vou mais tarde. Ali o ambiente. Não temos lá nenhum suficiente. Sei, mas tem.
Tens aí no canal.
As já estão desligadas, se calhar está bom.
Bem-vinda.
Obrigada. Eu posso contar com o senhor
À banca já estou.
entre o dia 24 a 26 de junho.
Vai ser de tal
Vai provavelmente nessa altura. Por volta das 13 horas da tarde, horário.
questão de confrontar. Deve ser difícil.
Obrigada. Você foi fundamental para isso.
Eu acho que a do trabalho fada, parabéns. Eu tive o gosto de estar a acompanhar o trabalho.
Mas foi essa ideia aqui do povo que deu.
Pronto, e agora? E a seguir já tem.
Good morning, everyone, and thank you all for being here and attending the second edition of the celebrations of the International Day of Light, organized here by the University of Porto SPI chapter. So before beginning all the events that we are all very aspiring to, we would like to first give a brief introduction by our one and only, our mentor, Professor José Luís Santos. So thank you very much, Professor José Luís. The stage is yours. Thank you very much.
Thank you so much. Thank you so much. If you don't mind, I will turn to Portuguese. It's okay? It's okay. O facto de ter a nossa própria linguagem permite um outro tipo de comunicação. A linguagem, digamos, mãe, permite uma outra comunicação que o inglês não permite. Portanto, estamos aqui com uma iniciativa do Chapter. O Chapter é uma iniciativa da SPI. A SPI é a mais importante e maior Sociedade Internacional de Óptica e Fotónica. Tem mais de 250 mil sócios em 170 países. Há outras, como a OSA, a I3R, a parte da fotónica, mas a SPI, de facto, tem um alcance global que nenhuma outra tem. Depois, a SPI tem também uma iniciativa que é ligada aos mais jovens, ao meio universitário, que são os chapters. Eu estive ontem a ver, a SPI tem cerca de 350 chapters ativos em todo o mundo. Portanto, o facto de nós termos aqui no Porto um chapter ativo deve-se, que se iniciou em 2012, deve-se a um conjunto de jovens que ao longo destes anos todos tomaram em mãos esta tarefa. Devo dizer que a pessoa fundamental para o início do chapter do Porto foi o Orlando. Eu sei que ele vai vir, porque o Orlando, de facto, foi a pessoa, digamos, que induziu a ideia, vamos avançar com o chapter do Porto. Pois, claro, teve vários presidentes, estou a ver aqui o Luís, o Nuno e muitos outros, e uma geração de ano após ano, digamos, novos estudantes, novas direções. Portanto, estamos aqui para celebrar o Dia Internacional da Luz, certo, não é? Portanto, e é sempre, antes disso, quero dizer bom dia, que bom vê-los aqui, não é? Todos vós, não é? Mas aqui os nossos convidados que já andaram por cá, não é? Que bom vê-los aqui, tá bom? O Dia Internacional da Luz é comemorado desde 2018 a 16 de maio. Bom, 16 de maio é amanhã, não é? Pedro também está ali, olá Pedro, viva. De qualquer maneira, como é sábado, fez o SPI Chapter do Porto, fez esse evento hoje. E porquê no dia 16 de maio? Porque no dia 16 de maio, este senhor, Theodore Mannen, tem aqui um brinquedozinho, aqui ao lado. Na verdade, neste dia, em 1960, foi a primeira vez que, neste planeta, tanto quanto se sabe, porque a Terra tem um histórico muito longo, não é? Que luz laser teve vida. Portanto, é um laser de rubi. Deve-se dizer que, e nesse sentido, o marco histórico, não é? Marco histórico, mas é uma coisa muito pequenina, que parece maior. É importante ter a noção de que a teoria do laser foi construída em 1917 por um artigo publicado por um senhor que conhecem, que é o Albert Einstein. Mas na altura percebeu-se que não havia condições ainda tecnológicas, demorou muito tempo a chegarmos a esse ponto. Portanto, qual é o tema? Todos os anos a Unesco define um tema para o Dia Internacional da Luz. Qual é o tema do Dia Internacional da Luz de 2026? É a luz para um futuro de sustentabilidade. Não poderia ser o melhor tema, no sentido de que estamos numa época muito turbulenta e, de facto, referenciar a luz, que é algo especial para um futuro sustentável para todos, é algo muito, muito importante. Subjacendo a tudo isto, uma pergunta se coloca, que é: luz, o que é? Luz, o que é? Bom, é muito engraçado hoje em dia que temos a inteligência artificial, fazemos perguntas à inteligência artificial para ver o que é que ela responde, que é um bom exemplo do que realmente se consegue obter em termos de perspectiva global. E a resposta é: a luz é uma forma de energia que se comporta simultaneamente como uma partícula e como uma onda. E depois continua. Fisicamente, a luz ela é definida como uma radiação eletromagnética que pode ser percebida pelo olho humano. É a resposta que dá uma plataforma de inteligência artificial. E agora, fazendo uma outra pergunta. Qual a importância da luz para o ser humano? E ela responde dizendo: bom, a luz é fundamental para a saúde humana, atuando como um motor biológico que regula o ciclo de sono, ritmo circadiano, impulsiona a produção de vitamina D, essencial para o sistema imunitário e para os ossos, e melhora o humor ao estimular a serotonina. Interessante. Portanto, certo, então a luz e a sua interação com o ser humano resulta em algo mais do que o simples processo físico de fotodetecção de fotões para o nosso sistema visual. Não é? Possibilitando a visão, que, como sabemos, é um meio privilegiado de interação com o meio ambiente. Mas a verdade é que também tem impacto em algo que não é mensurável. Por exemplo, nevoeiro na cidade, chuva na cidade, pessoas tristonhas. Dia de sol, pessoas felizes. Uma nota relativamente ao estado de espírito induzido pela luz. É um aspecto muito curioso, porque se passa despercebido, mas que já é utilizado em certos contextos, como tudo na vida, para coisas boas e menos boas. É sabido que, se estamos numa envolvência de luz vermelha, ela estimula uma maior atividade, poder, paixão, potência, um ritmo mais frenético. E constata-se que tem havido em certos sítios no mundo que, em ambientes de trabalho, coloca-se uma luz desse tipo, no sentido de pôr as pessoas a reagir mais intensamente. Em contraponto, uma envolvência de luz azul induz a sensação de paz, de confiança e de tranquilidade. Portanto, nitidamente, isto não tem a ver simplesmente com o ser visual. É algo mais profundo, se calhar. Não entendemos as razões para isso acontecer. Para além destas vertentes, portanto, uma mais direta relacionada com a visão, e a outra mais intangível relacionada com o nosso estado físico e emocional. Há uma pergunta que se coloca: tem a luz algum outro impacto no ser humano? E a resposta é um absoluto sim. Porquê? Porque a luz induz emoção. Induz emoção. Tem essa, não só a luz, talvez o grande rival da luz seja a música, possibilita chegarmos a estados, digamos, emocionais muito intensos. Sendo que em crescendo, é muito curioso, porque no século XIX e no século XX, digamos, divinizava-se a razão, não é? Entretanto, a coisa muda, percebe-se que nós não somos fundamentalmente razão, somos fundamentalmente emoção, não é? Sendo que em crescendo se compreende que a emoção é um pilar fundamental do que significa ser humano. Constituindo a razão, muito importante, um instrumento para compreender e controlar a forma como as emoções são expressas e para explorar os caminhos que ela abre, que não são caminhos de racionalidade. Portanto, a ciência, a descoberta de novas coisas da ciência não é só pelo raciocínio, não é só pela dedução. É preciso algo mais, há um salto que é a emoção que proporciona. Portanto, posso dizer, a necessidade de articulação destas duas irmãs é crucial. E uma boa educação para os jovens, para a comunidade, tem que ter em conta muito estas duas irmãs. Como nota, é muito curioso que a um nível de fenómenos é conhecido que a emoção pode desencadear o quê? Fenómenos biológicos que não compreendemos. Por exemplo, a comunicação entre diferentes partes do corpo, desde o cérebro à ponta do dedo, com velocidades que são incompatíveis com a velocidade, com a dinâmica de processos bioquímicos conhecidos. E estamos a falar de quê? Em situações em que o estado corporal se transforma agora, digamos, num estado de sintonia perfeita, ou sintonia completa. Isso acontece quando? Tipicamente. Quando estamos numa situação de healing, uma palavra que é difícil de traduzir para português, uma espécie de sintonia, quase uma conexão religiosa, digamos, mística, digamos assim, em situações de amor e em situações de medo. Em situações deste tipo, em que a emoção é absolutamente dominante, de facto, nós entramos em estados biológicos que realmente não compreendemos. Muito bem. Então a luz induz no ser humano muito mais que a simples interação da radiação luminosa com a matéria, certo? O que é que dizem as tradições espirituais universais sobre a luz? Se nós formos para o Oriente, portanto, ou seja, se juntarmos, condensarmos as grandes correntes, o hinduísmo, o budismo e o taoísmo, a luz não é apenas a radiação física visível. Na verdade, é um símbolo profundo de sabedoria, de consciência, de divindade e de pureza que dissipa a ignorância e a visão e representa a essência suprema do universo, o verdadeiro self, no sentido eu superior, que reside dentro de nós. E, na verdade, com variantes, o mesmo sentido evidencia-se em todas as tradições espirituais de todas as latitudes e longitudes. Ok, mas voltemos ao que a ciência nos diz, a ciência no estado atual nos diz sobre a luz, sobre o fóton. A eletrodinâmica quântica é uma das mais bem-sucedidas teorias físicas. Teve Feynman o seu, digamos, o seu elemento máximo inicialmente, depois foi desenvolvido ao longo do tempo. Portanto, é uma teoria que permite prever com uma precisão absolutamente impressionante os efeitos da interação entre as partículas e a radiação eletromagnética. Nesta teoria, assume-se a existência de um campo, chamado campo fotónico, que tem, por razões históricas, chama-se campo eletromagnético, que permeia todo o espaço-tempo. Diria, talvez, sendo mais correto, que está subjacente ao espaço-tempo. Ou seja, temos aqui o espaço-tempo e debaixo há qualquer coisa, este campo, que chamamos campo eletromagnético, campo fotónico. Campo esse que, em geral, está num estado de mínima energia, mas tem flutuações. Essas flutuações aparecem no espaço-tempo como, digamos, partículas, etc. Por decomposição de Fourier, grande Fourier, não é? Que está na base do modelo do oscilador harmónico, pode-se modelizar este campo como uma soma, portanto, um integral, de modos próprios, digamos assim. Professor? Viva. Cada um caracterizado por uma frequência de oscilação bem definida, ou seja, tempo bem definido, e uma orientação espacial bem definida, espaço. O que é que isto implica? Pela teoria quântica, esta definição exata implica que os níveis de energia desses modos são discretos, estão assim quantizados. Não é? Na teoria da eletrodinâmica quântica, o fóton é introduzido como a unidade de excitação do campo eletromagnético relativa a um determinado modo. Tá bom? O que significa que tem uma energia bem definida e uma direção de excitação de oscilação, digamos assim, bem definida, o que implica uma quantidade de movimento bem definida e uma polarização bem definida. Como tal, na descrição eletromagnética mais conhecida, isso significa que essa excitação se associa a uma onda plana monocromática. Portanto, ou seja, com uma energia, quantidade de movimento e polarização bem definidos. Ora, muito bem, invocando novamente a teoria quântica, que implica a completa definição destas grandezas tem como consequência uma completa indefinição relativamente ao espaço e ao tempo. uma completa indefinição relativamente ao espaço e ao tempo. Sendo assim, não faz sentido atribuir uma localização espaço-temporal ao fóton, parecendo que ele se situa por todo o espaço e por todo o tempo, em certas condições, materializando-se num determinado local e num determinado instante. Acresce, recordando um bocadinho destas coisas, que, ao contrário de outros observáveis da teoria quântica, não é possível atribuir um operador ermítico, seja com valores reais, ao fóton. Portanto, como acontece para os eletrões, etc. Ou seja, o simples conceito de localização e espaço-temporal tem de ser considerado com muita cautela para o caso dos fótons. Na verdade, e agora indo para a teoria da relatividade, todo o universo, para o fóton, todo o universo na direção do seu movimento está contraído num único ponto. Ou seja, para o fóton o espaço deixa de ter profundidade. E o local onde o fóton é emitido e o local onde é absorvido tocam-se, são o mesmo. O tempo medido pelo fóton não passa. Ou seja, o nascimento, mas a viagem e a morte do fóton ocorrem no mesmo instante. Na perspectiva do fóton, olhando para fora, cuidado com a nossa linguagem, certo? Todo o universo exterior está completamente congelado no tempo. Em termos de um exemplo prático da luz do Sol, nós vemos que a luz do Sol demora 8 minutos a percorrer os 150 milhões de quilómetros entre o Sol e a Terra. Na perspectiva do fóton, após o seu nascimento no Sol, atinge a Terra no mesmo instante, sem ter percorrido distância nenhuma. Algo é certo, nada disto encaixa bem nos nossos referenciais habituais. Bom, assim o que sabemos sobre a luz? O que sabemos sobre a luz? Sabemos que é composta por fotões que têm as propriedades seguintes. A propagação de fotões no vácuo está associada à velocidade máxima no espaço-tempo. Ou seja, para os fotões o tempo e o espaço desaparecem. Não tem massa nem carga. Os fotões estão fora do mundo material. Não têm dimensões. Não são localizáveis. Não é possível uma contagem precisa do seu número. Num feixe de luz coerente, cada fóton é indistinguível do outro. Tem um momento angular intrínseco. Transporta informação de fácil e impossível determinar o seu valor com exatidão. Com uma certa probabilidade, podem seguir qualquer trajetória do espaço-tempo. Não é possível conhecer exatamente a sua origem. Portanto, sumariando tudo isto, podemos dizer que coisa estranha. Este senhor muito famoso foi quem inventou, digamos, aquilo que nós podemos chamar a ótica quântica, com o Prémio Nobel da Física de 2005, faleceu não há muito tempo. Tem uma frase célebre a este propósito. Diz ele: não sei nada. Reparem este senhor, quem é este senhor? Okay? Portanto, desenvolveu toda a teoria da ótica quântica, ou seja, do laser, de uma forma exata, etc. Não sei nada sobre fotões, mas sei reconhecer um quando vejo um, que é uma frase curiosa. Não é? Bom, e o nosso Albert Einstein, que foi o pensador por excelência destas coisas. O homem pensava. Antes da sua morte, em 1955, escreveu uma célebre frase, que é assim: 50 anos de busca contínua não me aproximaram da resposta para a pergunta: o que é a luz? E depois acrescenta, é muito curioso. Certamente hoje em dia, em 1950, à volta disso, todos pensam que a resposta é conhecida, mas é uma ilusão. É muito curioso que em 2003, num número importante da Photonics News, dedicaram este número sobre, digamos, o número dedicado à luz e ao fóton. Então, os editores convidaram, na altura, as pessoas mais famosas, digamos, as mais conhecidas, digamos, nesta matéria, que são, portanto, tem 5 artigos destes senhores, nesta edição, e então, os editores, ao analisar os artigos, escreveram um prefácio, não é? Digamos, uma espécie de prefácio, em que diziam, bom, sobre a natureza profunda da luz, Estamos hoje no mesmo estado de ignorância esclarecida, obviamente sabemos muita coisa sobre a luz, como estava há 50 anos atrás. Muito interessante. Assim, parece-me que se justifica citar umas células palavras do Einstein, preferidas em 1948, talvez uma das mais famosas que ele tem. Diz ele, o mistério, não é? É a emoção. Cá está. Emoção. A emoção fundamental que está na base da verdadeira arte e da verdadeira ciência. E assim, inspirados com esta perspectiva, não é? A verdade é que temos conseguido coisas notáveis na compreensão e características da luz e, com isso, desenvolver toda uma tecnologia fotónica que tem revolucionado a sociedade. Olha, fibra óptica, com tudo o que significa, não só da fibra, do que está montante e jusante, digamos, em termos de tecnologia, a imagem, os lasers, certamente, a iluminação LED, que revolucionou completamente a iluminação, podemos controlar a iluminação, as aplicações médicas, a procura de coisas lá fora e todo o mundo. Muito interessante, meus amigos e minhas amigas, é preciso termos atenção neste ponto. Com perspectivas de inovação para os próximos 50 anos que nós não vale a pena tentar imaginar o que é que acontecerá. A nossa perspectiva de imaginar o futuro é linear, não funciona. Portanto, daqui a 50 anos haverá coisas que não fazemos a mínima ideia. Assim vamos apreciar este evento. Dia Internacional da Luz, por este chapter. Este chapter, que foi fundado em 2012, como eu referi, iniciativa do Orlando, que depois que teve, digamos, todo um processo de gestão, que eu costumo dizer, de gestão tipo Carlos Gulbenkian, que quem está no board executivo começa, vai subindo, chega a presidente em geral, pode ser, depois vai saindo gradualmente e sai. E é isso que tem acontecido nas direções do chapter, porque permite a continuidade. Estou a ver ali dois notáveis presidentes, o Nuno e o Luís e o Nuno. Né? E devo dizer uma coisa. O ano passado houve uma conferência aqui no Porto sobre fibra óptica. Esta é uma das fotografias de um conjunto dos red shirts, foram conhecidos como red shirts. Este senhor que aqui está foi um presidente da SPY. E a verdade é que sobre a coordenação ali, sobre a coordenação ali o Nuno, não é? A coordenação e o apoio e o gosto que eles tiveram, fizeram um trabalho absolutamente notável. E vou-vos contar uma coisa. Vocês, red shirts, ficaram na retina de tanta gente. E o que eu ouvi este ano, a ponto de, isto agora é uma surpresa, a ponto de, todos os anos, a SPY, nos seus 350 chapas por todo o mundo, faz uma seriação de primeiro, segundo e terceiro lugar, em termos das atividades do chapter. Pois acontece que, devido muito, digamos, à atividade, não só neste evento, mas muito por este evento e pelo impacto que vocês conseguiram induzir nas pessoas, eficiência, simpatia, as duas coisas. Fazer bem as coisas e fazer com carinho. Isso faz toda a diferença. Resolveram atribuir ao chapter, não é? Ao chapter, relativo em 350 chapters, todo o mundo, resolveram atribuir, portanto, o terceiro prémio. O terceiro prémio, né? Que está aqui, não é? Ao chapter do Porto pela sua atividade em 2025. Portanto, eu ia pedir a todos os red shirts, venham aqui, por favor. Venham aqui. Venham cá, todos aqui, todos, não é? Porque eu quero que peguem nisto e que se tire uma fotografia sobre isto. Está bem? Anda cá. Venham cá. A Diana. Mariana.
A Presidente é que deve.
Diana, anda cá. Isto foi o ano passado, eu sei. Agora põe-se só Muito bem. Tá? Muito bem. Portanto, vai ser colocado no sítio nobre. E, portanto, o que eu quero dizer, vamos apreciar este evento. E da minha parte, digo, é um privilégio ter tido a oportunidade de estar estes anos todos, na fase final da minha carreira, que teve como mestre este senhor que aqui está, portanto, vai para Pereira Leite. Eu com todo o gosto, eu sou discípulo dele, sabe? Eu sou discípulo dele, não é? E como contente eu estou por ver que isto tem um futuro baseado em vós. Portanto, resta-me dizer muito obrigado. Está bom?
And thank you, Professor, for your words. We'll start now with the two talks. This will be 30 minutes talks. I'll just ask the speakers to reserve a little time for questions and answers, the interesting part to talk about your work. And next we'll have the coffee break. So first we'll have Ricardo Ferreira with us from HBK Fiber Sensing. He focused on photonics and semiconductor engineering. He has a background, he obtained his master's from the University of Aveiro in physical engineering with a foundation in optoelectronics and optical fiber sensing. His professional career, he works on research and development and currently works as a sales engineer at Fiber Sensing. And he'll culminate all his academic and professional work to give solutions in optical sensing. So I ask you to come to work, and you'll be talking to us about monitoring with optical fiber gratings. Thank you. When you're ready.
Okay. This one, right?
Yes.
Okay. So this goes down. Okay. Hello, everyone. Thank you to the professor for the great presentation and start of the day. It's really curious that even though we don't know nothing about light, we find ways to use it for the better of humanity. So, as presented, I am a sales support engineer in fiber sensing as part of the optical business of HBK. Today, I will give you a presentation of the company, talk a little bit about our technology, fiber bright gratings, and also the optical interrogator. Some technological advantages of the technology and some more technical applications so that you can see that this is not only research, it is also applicable in the real world. And I will talk about future perspectives of the technology. So, fiber sensing was created in 2004. It was actually a spin-off of Inesc and it was specialized in measurements for fiber bright grating technology, developing sensors and also data acquisition systems. It was later acquired by HBM in 2014. HBM is was a well-known company for strain gauges, electrical strain gauges, and decided that our portfolio would have an extent to their applications. Later, in 2019, HBM merged with Brilliant Care, which is a company specialized in the manufacturing of vibration sensors and related to sound and vibration. And we are now part as HBK. So we are the optical portfolio of HBK worldwide. As you can see,
we have a great range of presence either in the United States, in Asia, some in Africa, and the majority in Europe. Every blue dot is an HBK site, and every orange dot is a distributor, an official distributor of our products. And fiber sensing is actually based in Portugal, here in Porto, now in Maya, in the new factory. And so we have a whole range of solutions from the sensor to the application of the sensor and the data acquisition systems. We focus more on the structural analysis platforms. So strain sensors, temperature sensors, acceleration, displacement, tilt, and load. We also manufacture the data acquisition systems, and we provide on-field installation and support together with customized customer solutions and training on our products. So I will not spend much time talking about fiber reg ratings. I'm sure you all know what it is, but it's always good to remember. We have incident light on the fiber. Actually, first, the fiber needs to be engineered, meaning we have to inscribe a microstructure inside the nucleus of the fiber so that it gives us some feedback on the interaction with the light. So after that, light enters the fiber, and then there is a pattern, a reflection, and the transmission pattern. And what is measured is the reflected pattern on the interrogator side. So it's a reflection acquisition. So as part of our single sensors, we have this whole portfolio of displacement up to acceleration sensors. And we also take advantage of the multiplexing capability of the optical fiber by delivering groups of sensors. Either the FPG, just the FPGs on the bare fibers, multiplexed in series, bundles of temperature sensors, and also a mix between strain and temperature sensors on the same fiber. Now, the optical interrogator, which is, I think, the best part in terms of technology, more interesting one. So I will present here the most recent interrogator that we have. It comes in two versions, the dynamic one, which is the MXFS DI, and the static one, which is the SI. They are both based on a tunable laser, which can reach up to 2000 Hertz of sweeping. We can have capacity of up to to measure up to 512 FPGs with a single interrogator. The dynamic range is the capacity that the interrogator has of compensating for the optical losses along the path of the optical fiber. So the MXFS-SI has a higher capacity of doing that. Resolution and stability are also two parameters that give us some kind of understanding on how the system works with temperature variations, and just by being there measuring how much will the measurement fluctuate. So the static one has a better output, so it performs better for those two characteristics. They are both interrogators. They use a smart peak detection algorithm, and this is one of the main advantages of using this kind of interrogator is that it can actually measure peaks as small as 3 dBs above the noise level of the interrogator. So we can actually have, for instance, an FPG peak of minus 40 something dBm, and it can still measure it with great precision. Also, it has an internal absolute reference, which which means that it doesn't need to be periodically calibrated. It is constantly comparing the measured value with an internal reference, internal NIST reference. And the spectral window is between 1500 and 1600 nanometers, compatible with optical communications fibers. So if we look at the skeleton of this MXFS, this interrogator, we have three main blocks. On the top one is what we call the OEA, the electronic assembly. This is where all the optical engine is. I'm blurring it because technically I can't show it to you, but I mean, you can still see there are some components there. It's where the lasers are, the filters, the optical isolators, the reference, everything is on the main board. Then on the middle board is the IBA. It stores in its memory all the information from the signals, from the calibration data. So everything is stored there, and it's also responsible for the amplification of the signal coming out from the photodetectors to the memory. And also on the bottom side, we have the SoC, which is, apart from having all the communication ports, it's also where everything is written and read, and the actions are performed in the interrogator. Yeah, looking at the building block, so we have a tunable laser, which is constantly sweeping in wavelength, and the light that comes out of the tunable laser goes to an internal photodetector for comparison with the reference. And some of the light, most part of the light, goes to the FPGs here, to the sensors, through connectors. The connectors, before the connectors, they have a circulator so that the reflected light goes directly to the photodetector and does not go to the optical engine, possibly causing damages to the system. So, some technological advantages of the technology. Because the fiber has very low signal attenuation, as you know, and it has a multiplexing capability, meaning we can have several FPGs inscribed in the same optical fiber. It is very suited for the installation on big structures and remote areas, such as pipelines, bridges, monopiles, and tunnels. It is also electrically isolated, immune to electromagnetic interferences, and passive. It's a passive technology, meaning that it doesn't spark. So you can use this to safely operate in hostile environments, such as high voltage, electrical turbine, gas industry, so on. We have a message there. So, because it is also resistant to humidity, salt, and pressure, it is perfect for offshore applications such as the wind industry and the oil and gas industry, etc. Ship hulls as well, for the monitoring of the structural health monitoring of the ships. So the multiplexing capacity reduces the total cable quantity as well when we compare it with electrical sensors, for instance. The fiber optics technology actually reduces a lot on the cable quantity, reducing weight and complexity of the system, and is for that reason used in high sensor count applications. It also has high fatigue limits and can be embeddable in materials such as concrete or any other material that can be embeddable. It is ideal then for new material performance tests, such as in the aeronautics, aerospace, and other innovative smart structures. A sum up of how it can help us. And now the most fun part is the markets and applications, because it's always good to see the technology applied on real case scenarios. So, one of our main markets is the structural health monitoring, either for short or long-term monitoring of bridges, tunnels, and buildings, critical infrastructures, so very important for the human being. They can also be used on onshore and offshore monopile monitoring. So in this case, I have a recent application that is still ongoing for the Gothenburg Tunnel in Sweden. It's a tunnel they are building for the metro line, so it will be a critical infrastructure. And we are using our sensors for the measuring during construction, during the blasting of the rocks. And also, the plan is to have the sensors there for long-term monitoring. There are a lot of sensors involved here and kilometers of optical fiber. This is a big tunnel that connects almost the whole city of Gothenburg. And there are plans for other tunnels in the future that will connect to this one. Another project was a bridge in Poland last year for the long-term monitoring of the bridge. It's a small bridge that connects the mainland with an island. And this was a very difficult application for our technical engineer because of the weather, because of the wet surfaces, the ice that was on the surface as well. So the sensors had to be welded, but it was very challenging for him to do this. Even though, I mean, he could do it, and it's proved to be a good installation in the end. So the sensors are there reading, so it proved to be a good application. Also, on wind farms in the Northern Europe, we have several projects there since 2020 that we have been working on them. Our sensors are used both on the blades and on the monopiles. The monopiles are funny because they need to be hammered down on the seabed, so it's not any sensor that can deal with that, and that's where the fiber optics comes. It's a very robust technology that survives this type of harsh environments. Another market we are on is the transportation market. For this case, we have a solution for a pantograph. The pantograph is what connects the train to the catenary, so it delivers power from the power grid to the train. And this kind of messy apparatus is very important for the train industry. They use it to test trains, to deliver power to the train, etc. And we have a solution based on interrogator, sensors, and accessories, a full solution that uses accelerometers and load sensors to understand exactly where the catenary is hitting the pantograph, and also how it is touching the pantograph by measuring force. With this information, the customer can actually actuate the pantograph and adjust the correct parameters so that no power is so that power is delivered correctly. Another market is the energy market. We use our sensors for the monitoring and maintenance of energy generators, power transformers, and also on battery testing applications. In this case, we have a solution for Siemens GenAdvisor. OEM solution, how we call it, is a solution with the branding of the customer. Okay, so the sensors and interrogators are manufactured in our factory, but they go out with the branding of the customer. In this case, Siemens. We developed a solution for vibration monitoring of their generators, and both the sensors and interrogators are customized for their application. We also have some R&D applications.
where sensors need to be embedded in composite materials or cryogenic application measurements, aerospace applications, and tests in medical components. In this case, I'm showing you the ITER, which is the International Thermonuclear Experimental Reactor. Sorry. This is in France, actually, and our sensors were used for the monitoring of vacuum vessels. But before that, they had to be qualified. So they were tested for radiations up to 10 megagrays, vacuum as low as 0.01 Pascal, and temperatures of 200 degrees Celsius. And they behaved correctly. And actually, in this case, the customer wanted to qualify both electrical sensors and optical sensors for the same reason. And we took advantage of HBK large portfolio and delivered them a solution based on both technologies. We also are seeing a growing interest in the medical applications, mainly in the instrumentation of their devices. So all the applications we have are confidential, unfortunately, but it's a trend that we are seeing. So medical, even though medical already applies optical sensors, they are trying even more to look for new approaches with optical FPG sensors. As a future perspective, we have a lot of applications on large-scale sensing networks, applications with a large number of sensors, but and also niche applications where fiber optics or FPG sensors are the only usable sensors. But we also have the objective of tackling the few sensor markets. So universities, conventional applications for a lab test or few sensors applications is something that we are trying to reach, but we can't reach that with the current interrogators that we have because they are expensive. They are built for large-scale sensing networks, and we are trying to reach that market by using new technologies and also old technologies and align them together to make less costly and more affordable interrogator. And for that, we are thinking about vertical cavity surface emission lasers, MEMS systems allied with that, and also photonic integrated circuits for this objective. Yeah, and thank you.
Okay, and thank you for your time. Yeah. We'll have now some time for questions. Who wants to start? Okay. There are other questions. Forgot about that.
I thought that was clear.
Talvez queria, digamos, não saber se uma imagem das novas instalações.
Sou capaz, tenho no meu telemóvel. Capaz.
Isto está em Vila de Conde, lá na Maia. Ainda é Vila de Conde.
Ainda é Vila de Conde, é verdade. Só que eu não sou daqui, venho de Aveiro, e para mim é Maia onde eu estou. Maia, Porto.
Não consegue estar aí.
Só se eu abrir o meu PC. Precisa de acesso à internet. Não vale a pena ter acesso à internet. Posso ligar diretamente o cabo HDMI? Ou não? Não? Se calhar não. Depois sim. Eu envio.
When you mentioned that you are interested now to progress with the technology, including MEMS, integrated mathematics, etc., are you looking for collaboration partners, or is this something you do on your own, or is this done within this big network like HBK?
Yeah, we actually look for collaboration partners, but we also do that. I mean, we do not develop the VCSELs and the MEMS ourselves, so it's always looking for what's on the market. So yeah, that's it.
One follow-up question. I mean,
Yes.
you explained it, but like you now here in Porto, like how big is the team, or how? You mentioned in the beginning, and that you work as a freelancer, independent.
Yeah.
Person. So I think that's interesting for us to know about this career opportunity.
Yeah, the team itself, just for the optical business, we are around 100 and something, but the whole HBK is vast, is big. And we also have people working for HBK, but not on the optical business in Porto. So it's also important. It's a cluster, important cluster for everyone that is working from Portugal to the main HBK offices. So there's always opportunities.
Okay.
Ok.
Any more questions? Okay.
Eu posso tentar procurar as instalações aqui na.
Isso era interessante. Realmente, digamos,
Thank you.
antes de haver empresa, que é uma coisa, eu acho que é impossível. Eu sou um bocado suspeito.
Aqui.
Ok.
Funcionistas têm que ser.
Posso ir ao LinkedIn?
Sim.
Eu ponho aqui. Pode ser uma imagem do Maps. Se calhar pode ser que existam imagens.
Não, é ficar tipo esmagado.
Para a próxima já sabes.
A próxima tem que ter uma imagem. Ok. Mas pronto. Isto são as novas instalações vistas de fora. These are our new installations seen from the outside. They are. I don't know if we have. This is Luís Ferreira. Or C.
Pode explicar que Luís Alberto.
Como?
Luís Alberto was a student.
Luís Alberto. Yeah. He was a student here, one of the founders of Fiber Sensing. Unfortunately, I don't have. I can show it in the end.
Okay.
I will look for it.
Mostra lá o gabinete de São Luís.
This one. Okay.
Arribei.
Okay. Next one.
Quem vai deixar o nacional de
Aqui.
universidade?
Low resolution, but. Okay. I'll try to find a better picture.
Let's thank you.
Consegues pôr?
Okay, and now for the second talk, we have with us Dr. Marta Ferreira. She is an experienced researcher with more than 15 years in optical fiber technology. She has her master's from University of Aveiro in physical engineering and her PhD here in Porto with us. She currently is the coordinator of the Nanophotonics and Optoelectronics group at I3N in Aveiro, and she's going to talk to us today about the enlightening batteries with optical fiber sensing. So, when you're ready.
Perfect. Thank you so much for the introduction. Good morning, everyone. It's so nice to be here 10 years later. Jesus, 10 years already passed. And I must say that I see some familiar faces and we grew older, but you look fantastic, even after 10 years, I must say. So today I will talk about what we've been doing over these last 10 years. ICN. Okay, so I will give you just a brief introduction about I3N, talk about the nanophotonics and optoelectronics group, so the most important group there, at least from my point of view. I will then move on to a different topic. Today we heard a lot about light, about photonics, about the applications of optical fiber sensors. I will speak about batteries. So I will give you a brief introduction about how they work, what we can measure with optical fiber sensors, and then some takeaway message. And actually I forgot to thank SPIE student chapter for inviting me. I'm so sorry that I forgot, because I just get carried away, you know. And Carolina, I don't know where she is at the moment. You're there. Sorry. Thank you for the invitation. And Carolina told me it's going to be a talk directed to students. So my takeaway messages are for the students mostly, I hope. So IEEE stands for the Institute of Nanostructures, Nanomodeling, and Nanofabrication, and currently it has 2 hubs. One in Lisbon and one in Aveiro. It was created 20 years ago, and we cover different areas from material science, applied physics, to condensed matter physics, and so on and so forth. These numbers that you see here from a couple of years ago, they fluctuate a bit every year, but we are around 250 people in both hubs. And our work needs to be somehow connected into one of these 4 thematic lines. So the first one is sustainable micro nanofabrication, then green and clean energy systems. The third one is nanomaterials engineering and functional interfaces, and finally biomedical applications and systems. Here I will focus, the work that I will show today is more focused on the first and the second thematic line. Regarding the nanophotonics and optoelectronics group, we are a small group. I am currently the coordinator, together with Paul Antunes. He's the co-coordinator. We are 12 PhD researchers among professors and investigators. We have 10 PhD students, and these numbers, the master's degree and bachelor's degree students also fluctuate, but it's more or less 10 of each every year. And we go from the fundamental optics and photonics in our lines of research, like modeling and simulation for optical communications, for example. And then we enter the design and simulation of new sensing configurations. This is our core, I would say, at the moment. And we focus on the development of the different optical sensors for a broad range of applications that can go from biomedical, structural health monitoring, industrial processes, environmental, and the one that brought me here today, energy. And when I was challenged to do this, I started thinking, okay, what have we done over these last 10 years? How is our own timeline in these optical fiber sensors for monitoring batteries? How did it all start? It started actually with a Chinese guy, Yang Gang. He was visiting us at the moment, and he wanted to measure temperature in a coin cell. The coin cells are the ones, the very tiny ones, or a bit larger maybe, that we also have in our watches, so those small batteries. He was quite successful. It was the first time that a temperature was measured inside the battery with a Bragg rating. So it was in 2013, Yang Gang. And then we had our first participation in a European project, CERBAT. And in 2015, Michael and Susanna, you all know Susanna Novaes, she's with you currently. So they did a part of their PhD studies within this project. And then in 2016, I joined also during this project at the final stage of the CERBAT project. And then we had a gap with no funding for this part of work. In 2021, we were also invited to be a part of this consortium that was funded for the European project Instabat. And yeah, we had master's degree students, Fabio and Pedro, and then Luca. Luca is finishing his PhD next week. So yeah, Luca also joined us. He's a very bright student. And then João started his PhD in 2023 as well. Then Daniel. Daniel is also here. He did his master's degree thesis with us. And last year we had Carolina and Tiago also working with us during their master's degree thesis. And last year we also got this Enigma project approved. So in the end, we already collaborated with different partners, both from research institutes and also industry, because yeah, somehow batteries are a hot topic. I don't know exactly why, we will see in a moment. The FCT project, it's a small project, but we are really happy to collaborate with Maria Helena Braga from Matter group here in FEUP. So when we talk about batteries and when we talk about storing energy, we need to think about scale, right? We can go from the portable electronics, so kilowatt hour scale in capacity, so from watt hour scale to kilowatt hour scale if we talk about an electric vehicle like a car, and if we go to the renewable energy sources that we need to store somehow that energy, right? We can be talking about megawatt hour energy. So yes, we need to really find the best materials and the best way to store this energy properly. And if we focus on cars, just as an example, you know that the batteries in the cars are located on the floor, right, of the car. So the whole floor typically is covered with batteries. And this is, yeah, we have several batteries which are connected like this. So we have a pack of batteries, and a pack is made up of a combination of modules, and then we go even a bit into more the individual cell that we can get, a cylindrical cell in this case. Actually, Tesla is using these types of cylindrical cells in their cars. We can also have other geometries like the prismatic cell. So in this case, it's with a hard casing, okay, so really big cells. And then the easiest ones to produce and the ones that are usually studied in projects, as far as I know, are the pouch cells. They are flexible and they are easier to produce at lab scale. And here you can see, when I was doing the presentation, I promised you it looked really well and I could read it. Maybe for you it's not so easy, I'm sorry. But yes, this is these are some. You can have a look inside the structure. So to create the pouch cell, it's quite easy. We just need to stack some components like the cathode and the separator and the anode. I will speak briefly about it in the next slide. But when we talk about the prismatic cells, sometimes these are they are stacked. Sometimes they start to be rolled so that we have higher. It's a better geometry so that we can collect the most, use the area, the active area in the best way. And then the cylindrical cell is quite funny because it has a jelly roll inside. So imagine we have 3 sheets of paper and we start rolling it, okay? So we have these very beautiful layers. I will show you later on that they are quite interesting to look at. I hope I'm not bothering you a lot. I promise that I will try to be as brief as possible here so we can have a look inside one of these cylindrical cells. And you see that there is an anode current collector, and this is typically a copper foil. And we coat this well, not we, I've never done it, but some people coat it with a porous anode, which is typically graphite. And then we have this microporous separator. And this separator is really, really important because it makes sure that we don't have the anode and the cathode touching each other and creating short circuits, which we don't want. And then we have, on the other side, a cathode current collector, which also has this porous cathode deposited on this aluminum foil. And then the electrolyte that does the magic. Here is some presentation, some animation of what's going on inside the cell. Although I don't like it that much, but I think that it's we can understand quite well. So this is an electrochemical device, which means that we have chemical reactions inside. So when the battery is discharging, the lithium, there's an electron that leaves the lithium atom. So we had on one hand electrons and on the other hand lithium ions. So the electrons go in this direction externally, from the anode to the cathode, whereas the lithium ions go internally in the same direction. Okay, and when they reach the cathode, they recombine. So the electrons that were coming in this direction recombine here with the ions, with the lithium ions. So lithium becomes here again happy with the zero charge, and then during charge, the opposite occurs. So lithium ions are moving in this direction, whereas the electrons go in the other direction. And actually, at some point, these materials here, with this lithiation and delithiation, undergo structural changes. They change their geometry. I'm missing the word right now. They change their phase. Okay. There are some. I have no idea how long I have. I hope that I'm not.
15 minutes.
Okay, I will try my best. So we have several parameters that we need to understand. First is the how we charge and discharge, and how we apply charge and discharge cycles to the battery. So we can do it with a constant current, like the current is constant and the voltage is slowly increasing, or with a constant voltage. So the current is changing and the voltage is kept constant. We, in the end, have this kind of figure, which I think is quite important for you to have a look. So here, for example, we have constant current and the voltage is increasing. So the curve here for current is constant. In this case, this protocol, they kept then the voltage constant and the current started to decrease. So the battery here was discharging, starting to this one is still charging, but here it starts to discharge. So constant current and the voltage changes, so it's discharging. Also, another important parameter is the C rate. C rate essentially means that it's the current divided by the battery capacity. So it's a way that we can compare different cells because different cells have different capacities. And so 1C means that we are charging or discharging our battery for 1 hour. Okay, whereas in 2C, so if the C rate is 2 times higher, it will be faster, this process, so it will take half an hour. On the other end, if we are using this C/10 C rate, it will take 10 hours to charge or discharge. Now moving on to sensors. So this was our first step with the very well-known Bragg ratings. I'm not going into details. Ricardo already spoke about it. Here is the spectrum of 4 gratings that were used at some point to measure temperature. And we started combining with other sensing elements. This was our first work in CIRBAT, and yeah, it was a Fabry-Perot interferometer we just made with a fusion splicer and with a single mode fiber and a multi-mode fiber so that during the splicing we could create this air cavity with a very nice two-wave interferometer type of spectrum. This is the spectrum of both connected in series, and here comes the first thing that I would like to point out. When we were in the lab here, we made the calibration and everything was perfect. The sensitivities were exactly what we were expecting. And then Michael went to Germany and made the experiments and everything was a mess. The results didn't make any sense whatsoever. And we were really confused at the time. It was the really beginning. We didn't know how the materials would behave. Then we realized, oh, we need to calibrate again because the calibration is no longer valid when we introduce the fiber in a battery. So yeah, we calibrated again and we made the math and we got these curves. And in these curves, you can see the black line is voltage. And then on that graph, you can see the temperature variations. And then here, strain variations, because our sensor was capable of detecting both temperature and strain. And yes, although we are talking about 2 degrees Celsius in variation, which is not that high, and strain is really, really low, it was a pouch cell, and it was really one shot, and it worked out quite well for this proof of principle. Probably if I would do the work now, I would change a lot of things, but yeah, that's life. And you can see that there is a pattern somehow. Maybe you can see in the next slides a bit more with other sensors. CIRBAT ended. So as Professor Rodrigo says, Rodrigo Martins, our coordinator at IEEE, no money, no party. And we were like, we have no money, we have no collaborators now that we can go there and make batteries, and what should we do? Then we started thinking, okay, let's have a look into commercial batteries, at least to understand a bit better how this works. So we started, we made this pack of 3 smartphone batteries connected and had a look on temperature profiles because we were only measuring externally at the time. We had no idea how to introduce fibers in a battery, in a commercial one. And we made these gradient maps. We were quite happy. We would see at the end of discharge and at the beginning of discharge and also during charge. And we saw that, of course, as expected, that the batteries that were in the middle, there is no way for temperature to dissipate, so they heat a bit more. It was quite interesting, I think, this work. And then ISTABAT followed. And then again, we had a lot of partners and we had a lot of things going on. So this is one of the sensors that we developed and that we applied in batteries that were produced by our partners and also in commercial ones. So it was I would say a baby step from my point of view, but when we look at the broad perspective, this was quite awesome. So we made a Fabry-Perot interferometer. In this case, we wanted to measure pressure, not so much strain. So we wanted to measure gas pressure. And here you can see this diaphragm is made of glue, or UV curable glue. So our spectrum, and then we did calibrations and so on. And then we went to a globe box and we were able to drill a hole in the cell, place our sensor inside, seal it somehow, pray for the best, and we really prayed. And then we went to a micro CT just to check if we didn't destroy everything. And you can see here, I hope that I can convince you that this is void, this is hollow. This is where our sensor was. And here are those parts that I've told you before, those foils that are rolled up in a jelly roll. So we made this nice, this is Luca's work, this very nice data analysis app, and you can see here the voltage, and then here you can see this, the sensor's response, and here is already pressure and temperature, okay, so it's discriminated. And you can see, I hope to convince you, that there is some periodical behavior in both parameters. So when we have temperature, we have these fluctuations that are, not so nice, but then at some point, at the end of this charge, always, we have a maximum of temperature. So the temperature increases because it's an exothermic reaction. But then pressure, this is a lovely graph, right? It follows so nicely the voltage signal. But then we discussed with the partners and they were like, why is the pressure, it seems to be increasing, right, the baseline? And they were like, your sensor is wrong. You did something wrong. Your sensor has hysteresis. Your sensor is the worst. You need to do it again. You need to think about other ways to do it. And we were like, but why? Our sensor is so nice and lovely. And, you know, so we did some more experiments to check if it was hysteresis. It wasn't. And we didn't understand what was going on. And then Michael went to this conference, and there was this lady from the US talking about her work. And she said, you know, while the battery is operating, there is this solid interface formation, so this layer, that is irreversible. And also materials change in I'm missing the word again. Their phase is also changing, but there are some processes that are irreversible, and that can lead to pressure increase. And you're like, oh, wait. And Michael went to speak with her in the end, and she said, yes, definitely, that can be related to the material. And we are like, oh, this is good. Now we have a response to our question, our doubt. It was quite nice. So let's have a closer look. No, two buttons and I don't know which one to touch. It's always the same. Let's have a closer look here at 3 cycles. You can see that as the battery is being charged, so voltage increases, pressure also increases. As the battery is being discharged, pressure decreases, gas pressure. And it's always this movement, like the battery is breathing. So we have this breathing profile. It was already observed with other techniques, not only with fiber sensors, but we saw it with our sensors. It was also another glorious moment in the lab. So we did another, I won't go into details here with this incremental capacity analysis, but what I would like to point out, these dotted lines here are related with our sensor. And you can see that there are some connections in these 1, 2, 3, 4 rectangles. These are related with phase transitions of the material that were detected via X-ray diffraction. And with our sensors indirectly, we can measure, we can see that the material is changing. And bear in mind, this sensor is not in contact with the material itself. It's in void. It's just measuring pressure. So this was also, it shows the potential of this sensor, and this is why so many people are interested right now, and it's really, really a very hot topic using fiber sensors to monitor batteries, because you can have access to a lot of information in real time, in operando, without needing to destroy the sample, hopefully, or without needing to stop the charge and discharge and go take a measurement and come back and so on. I'm going backwards, that's the problem. So I still have a few minutes, right?
So,
Yay! Long-term stability experiments made during a period of 24 months because we wanted to check if our fiber would react with electrolyte or the other way around. I would like to remind you that this is a lithium-based electrolyte with fluor as well, and you can, well, if it interacts with the atmosphere, it can generate HF, which actually was one of my first works there, was to create a sensor that was able to detect HF, early stage detection of HF into batteries, which was patented in the meantime. And yeah, we checked over time, and you can see that there are some fluctuations that are actually linked to the environmental changes, like we are in summer, temperature is higher. We are in winter, temperature is lower. It's not so much related with the sensor being somehow degraded over time. And we also took some long-term, some pictures and at SEM to have a closer look on the fiber at different stages. So in the beginning, and then 3 months, 9, 18, and 24. And you can see that the fiber survives. It's still there. It's still the same size. It's perfect, but we can also see those lovely crystals forming. They are like small cubes. They are really, really cute. And yeah, this is the electrolyte crystals that are forming surrounding the fiber. But still, it worked. So we were also happy. So my takeaway message here is sometimes you just have one shot. You have to go for it. You shouldn't be scared. You just need to prepare yourself and prepare very well the work that you want to do. Okay? And this one shot can change everything. So use it well. No money, no party. Definitely. But there are still many things that you can do. You just need to think about other ways of solving your problems, especially when you are doing your PhD studies and yeah, you need to finish it. So there are always options. Baby steps can help you take a big leap. I didn't have this idea that 10 years ago we were just measuring temperature and then suddenly we are checking for material changes in a battery. But when I was, as I said, when I was preparing this talk, I was like, God, we did a lot of things over these last 10 years. This is just a brief overview. We did a lot more that I'm not showing you here. And this is this is very dear to me. Learn how to speak the different languages. It's very different, although we all speak in English or in Portuguese or whatever our mother tongue is. When we are talking with a chemist, with a material science, with a theoretical physicist, with an experimentalist, the language is always different. Sometimes we are talking about the same concepts, but in different ways, and we don't understand each other. And it can be really, really challenging. And because the typical reaction is, if you find something new, is no, you are wrong. Do it again. No, your sensor doesn't work. No, it's noise. And you see the noise happening every time. And you're like, it's a noise that it keeps repeating itself. So in the end, when you are collaborating with different people from different backgrounds, you need to be very, very patient. And that's all from my side. I'm sorry.
Okay, so we have time for 1-2 questions. Want to start?
Well, let me test your speech. Can you understand the theoretical physicist?
I will try my best, I promise.
Well, you put this fiber to sort of find the diagnostics of
Yes.
what you want to achieve. Charge a battery as much as possible and as quick as possible. And this is what I got from your presentation, which was very clear. So, but would you envisage a situation on which you could use the fibers or whatever other device with open fibers to achieve the very goal you want to, let's say, to help batteries to be charged faster. Because you have shown that there are some crystals that are showing up, so they have charges as well. I mean,
Indeed, indeed. The main goal in my case and in our work is not so much trying to charge faster, it's to understand, because it's really fun. Batteries are around for so many times, so long, and people still don't understand exactly what's going on inside. This is quite strange for us, indeed. And there is a lot of research going on with materials and searching the best materials for the best battery. Maybe this is where more or less the research in Europe is trying to go at this moment. So I would say that our goal here is to try to give a complementary view on what is happening inside the battery. Not so much our sensor will save the world, more our sensor can help other people understand a bit more what's going on. And as it responds so well, it responds when we have higher C rates, so the battery is charging fast, or even when it's slower C rates, so we can understand really what's going on in the material from the materials point of view. So it's a nice choice, and although it's not so easy sometimes to convince people that it actually works.
Okay. Any more questions? Okay. So let's think again. Okay.
I still have one question.
Thank you for the talk. I found it quite interesting. You showed that you put the fibers just in the point inside the cylindrical cell.
Exactly.
But do you think that there would be a benefit to later on deeply integrate more the fiber
Yes,
with the
definitely.
maybe even stick it in the back of the electrode plates? Or do you think this would ruin the pressure measurement?
No. We also did some experiments in that direction. As I said, the people that are researching in this field, they are really interested in understanding how the materials, when they use new materials, how they react. So there is a lot of research in placing just the fiber in one of on the cathode layer or on the anode. It depends on what they desire. But definitely, yes, there is a lot of room here. The thing is that these experiments are really, they take a long time because you need to do the sensor, to calibrate, to introduce the fiber, and then to make these cycling tests. They take long time. So when you are a small group, you need to think carefully about what to do.
Okay. No.
Now.
Okay, so now we'll have a coffee break and we'll be here again 10 minutes past 11. Okay, thank you. And it's the physics department, room 013.
ali na sala de espera. Tipo 10 minutos a deitar a na sala de espera.
Apanhei uma foto.
Só vi agora. Oh, ficou bem
Tá
bem.
fixe.
Bom dia.
Bom dia.
Pronto.
Conseguem ouvir?
Consegues nos ouvir bem?
Consigo ouvir bem, sim. Acho que sim.
Eu acho que nós não vamos conseguir ter a câmara ligada, porque ela está a ser usada para a gravação e não deixa de estar nos dois sítios ao mesmo tempo.
Tá. Então querem que eu partilhe o ecrã para ver se funciona?
Sim, pode ser. Podemos já testar.
Isto atrasou um bocadinho, uns 20 minutos.
É isso.
Portanto, nós vamos tentar compensar com o coffee break que era antes.
Ok. Então começa quando?
Pelas 11h10, provavelmente.
11h10. Ok. Então vou aqui partilhar o ecrã. Ok. Assim?
Sim, conseguimos ver.
Vamos só ver se eu meter em. Ok. Sim, bem em grande. Está bom, certo?
Sim, é assim, acho que assim está bom. Vê-se tudo.
Ok, perfeito. Então pronto. Então, 11h10, é isso?
Sim, se calhar por volta das 11h10.
Sim, sim.
E
Ficou marcado.
então entro neste link.
Sim, pode ser neste.
Está bem. Se calhar fico já aqui, não? Não sei se isto vai desligar ou não, mas posso ficar já aqui. Deixo a câmera desligada e espero que me chame.
E depois liga a câmera só.
É isso.
Se calhar é mais fácil.
Está bem. Então fico aqui à espera. Quando quiserem, digam-me. Estou aqui.
Quando for, nós mandamos um aviso ou uma mensagem aqui no chat.
Está bom. Perfeito. Obrigado.
Pronto, obrigado.
Até já, então.
Até já.
Era esta a surpresa do Zé Luís. Era a moldura.
Seja, quando eu for.
Oh, ouço muito mal, não sei se estão a falar comigo, mas ouço muito mal.
Não, estava só aqui a explicar uma coisa.
Ok, ok, ok.
Ah. Emanuel.
Sim.
Podes então partilhar, se calhar. Vamos
Uhum.
começar entretanto.
Ok. Uhum. Vou partilhar.
Se quiseres podes ligar a câmera, nós aqui não conseguimos ter do nosso lado. É isso.
Ok. Então, quando eu puder começar, digo.
O Tiago vai só falar aqui e quando
Obrigado.
ele diz.
So, hello everyone. Welcome to this second session of the International Day of Flight. So on the first part, we have some presentations related with optical sensors and fiber sensors. And so on this second part, we'll look more into optical computing and quantum optics and some information related with that. So our first speaker is Emmanuel Cruzeiro, which has a large background in quantum technologies and photonics. He has a PhD from the University of Ginebra, and Goran is an assistant professor in Instituto Superior Técnico and the coordinator of laboratory quantum photonics laboratory at the Institute of Telecomunicações. So he has a lot of experience in quantum optics, quantum light matter interaction, and today we'll give us a talk with the title Quantum Correlations and Communications. So, Emmanuel, you can start.
Thank you very much for the nice introduction. Hello, everyone. First of all, thank you for inviting me to this event. Unfortunately, I couldn't join physically. I enjoy a lot going to Porto. I have colleagues there, so I try to take advantage of that to meet the colleagues. But unfortunately, this month there were too many events, and I really couldn't join. So thank you again for the invitation. So today I'd like to tell you a bit about my preferred topic of research, which is quantum communication, and it has to do with something called quantum correlations. So this talk is going to be a bit of an overview and quite introductory. So feel free to ask questions if you need extra detail, and also feel free to contact me afterwards for any references that you might need or further questions. I know that we're a bit far apart, but if you ever come to Lisbon, feel free to write to me and come and visit the labs and meet the team. Okay, so I just wanted to show you here this drawing on the bottom right corner. So this is a drawing of a quantum internet. You might see in my background, but I will show you the image on one of the slides in a higher resolution. But essentially, it's this drawing, both this drawing and the picture behind me, are showing what will be a quantum internet in the future. Quantum internet will include fiber links, satellite links, and I will tell you a bit about that also today. So first of all, I don't know if everyone in the room is familiar with quantum physics, so I'll just briefly introduce a bit what's the story behind these quantum correlations and quantum communication. In fact, quantum information and quantum technologies. So this, of course, this first slide is very introductory. This is what I show usually even to kids in high school. So this is usually what popularization journals show as representations of what is a particle, for example. So this would be kind of something which is in between a particle and a wave, right? But in fact, as some of you might know, if you've had quantum mechanics is a recipe. It's like a book of rules that you have to use if you want to predict observations when you measure physical systems, okay? And it's probabilistic. It's based on computing probabilities via something called the Born rule. So the three basic elements that you need for quantum mechanics, there are other elements, of course, but let's say the most basic elements, you need a physical system, which is described by a quantum state. You need a quantum measurement that will act on that system. And then, so these, both the states and measurements have some mathematical properties. They are matrices. They are positive semi-definite matrices. They have other properties too. Okay, they have specific properties which make them physical. So so some matrix with specific properties like the positive semi-definiteness means, so if the matrix satisfies all these properties, it means that there is a physical system which can exist in that state, okay? And then the measurements also have all these properties, and then you combine both through the Born rule, which allows you to predict what's the probability of obtaining different measurement outcomes when you measure a particular quantum state, okay? So those are the three basic ingredients. There are also transformations, like things that transform states or measurements. For example, unitary operations, CPTP maps, but that's additional detail. Let's say that the basic rule book is what I just told you. So this whole book, or I guess this whole framework or theory was basically developed and established between the 1920s and 30s. So the first, of course, there was the photoelectric effect work by Einstein in 1905, which was proof that light can act as a particle, can behave as a particle, and was behind essentially the discovery of quantum mechanics. And around the 1920s, so during that decade, basically, mainly the physicists shown in this picture developed what is now today called standard quantum mechanics or textbook quantum mechanics, okay? So there's Heisenberg, Dirac, Einstein, Schrödinger, all those guys. At the time, there were not so many people working in quantum physics. Okay, around the 1930 or a little bit after, people were quite satisfied with this theory, in the sense that previous observations which could not be explained with other theories were now explained. And in fact, we didn't have any idea of experiments which did not satisfy this new theory. So seemed like a pretty successful theory. However, as you've heard for sure, and as you might know, there are some interpretation issues, and this has led to a lot of discussions over the years. In particular, right after this period of time where essentially quantum mechanics was fully developed, quantum mechanics as we know it today, Einstein, with two colleagues, so in 1935, came up with this paper essentially claiming that quantum mechanics could be incomplete. So what does that mean? Incomplete in the sense that the quantum states would not be describing everything that the physical system actually should be described by. So there would be some missing variables called hidden variables that were missing from the theory. So of course people were always listened to Einstein, right? He was an amazing physicist, but this seemed a bit probably to most physicists as a more philosophical kind of question that Einstein was putting here. So the idea was that you have physical systems, so meaning that mathematically you can check that in the theory there exist physical systems which are composed of many particles, but for which there are correlations which are very strong and arbitrary of the distance. However, like locally, there is no information in the states. So essentially, you know nothing about each particle, but you know that if you measure one of the particles, the other one will be, for example, in the same state. There's a very strong correlation, okay? So Einstein, when he noticed these states, and he was not the only one, there was also in the same year a paper by Schrödinger, which essentially came up with the concept of steering, quantum steering, which is how it's called today. Quantum steering is like you measure your half of an entangled pair, and so based on your measurement result, you will prepare a specific state on the other side, okay, on Bob's side. So, of course, like if I put it like this, it seems like there's some action at a distance. So this was precisely Einstein's attack on quantum theory at the time. It was to say, there's this, as he called it, spooky action at the distance. I don't buy it. Quantum theory must be incomplete. Okay. The argument had to do with a notion of reality that he came up with. So it's a complicated paper. I usually explain it in my PhD course on non-locality in Technic. Feel free if you have questions or want to understand better this paper, which is a very tough paper, I would say. Let me know. So, okay, there was this attack, let's say, by Einstein, as the New York Times put it. But in fact, for 30 years, almost no one did anything about it. This is a bit, I'm simplifying a bit. I mean, von Neumann did a lot on hidden variable theories. And there was this impression that indeed one could come up with hidden variable theories to complete quantum mechanics in a way. But the real, let's say, the real progress came 30 years later, almost 30 years later, in 1964. And I will come back to why 1964 in a minute. But I just want to say that from 1964 until today, we entered what is called the second quantum revolution. The first one was when the framework was developed, the full framework of quantum mechanics. Well, the textbook framework. Because quantum mechanics is still being extended, of course. For example, we don't know how to describe large physical systems with quantum states. So that's something that in the future we will understand better and better. But when I say that quantum mechanics was fully, let's say, formulated, I'm talking about textbook standard basic quantum mechanics. So from 1964 to today, we entered the second quantum revolution, which is characterized essentially by quantum theory now producing, enabling us to produce new technology. So it becomes actually useful in practice for society. And what are these technologies? Well, there are many of them. There's the quantum computing. Oh, sorry, by the way, some of my slides are in Portuguese, some are in English, but I hope that's okay. So quantum computing, you've surely heard a lot about that. So the quantum computer looks like this here on the right. This is a superconducting qubit quantum computer. There are other types. For example, there are photonic quantum computers, and these ones don't require cooling. So this one is cooled to very low temperatures using liquid helium, the one you're seeing on the right picture. On the left, you see a chip, quantum computing chip, which is essentially placed in the center of this cryostats, these big refrigerators. So you've heard a lot about quantum computing for sure. Even 2 weeks ago, there was a huge result 2-3 weeks ago, which essentially implies that very soon there will be a quantum computer that can essentially break a big part of modern encryption systems, which is related to an algorithm called RSA. So basically, the rush to have a quantum computer is driven today essentially by security and by the fact that the organization or whoever will have a quantum computer first will be the first to have access to some information which was supposed to be secret. And we don't know what these informations are. You know that governments and companies store data for decades. So this is like, it's called a store now, and decrypt later when you have a computer that can do it. Okay. So in principle, in 2029, that's what Google announced, and I think it's quite reasonable. And there will be a quantum computer in the world which will be able to crack RSA. Then there's quantum communication, and I'm going to tell you more about it in a minute. It will be the main content of the rest of the talk, which is about communicating with few particles of light. Okay. Then quantum crypto, which is very related. It's about guaranteeing security in communications. Not only in communications, in fact, you can, in some situations, you might want to guarantee security in computation. For example, imagine that several people want to compute something, but they don't want to share what their local data is. So each one has some data, and they want to compute something together based on all these data that people have, but each person doesn't want to share their information with the others. So that's something called secure multi-party computation, and it's also part of quantum cryptography. Then there's quantum metrology or quantum sensing, has to do with producing sensors and protocols for sensing, for measuring physical observables better than we can without quantum mechanics. Then there's quantum thermodynamics. You can ask questions like, for example, what is the smallest fridge that you can possibly come up with? And that is made of 3 particles. This was one of the first works in quantum thermo. It was already like 15 years ago, I think. And then there's quantum biology. Quantum biology is quite interesting. It's harder to have experimental data that you can analyze, but there's some really cool results. For example, now you can create a qubit, like as you create in a quantum computer, but in a fluorescent protein, and in a fluorescent protein that can live inside cells. So this means that you can have qubits inside cells, and using these qubits, measure what is going on inside the cell, in the whole cell environment. So this is like opening up a lot of new directions of research and technology. And also, for example, there's these ideas that essentially, like today, if we want to think about what's the best way of computing, several computers processing information by communicating with each other and doing local computations, then the best way we know how to do this is to use, I'm going to be a bit technical, but to use nuclear spins to do the computations and photons to carry information from nuclear spin to nuclear spin. And in fact, there's people proposing that this is how the brain processes information. There's quite a lot of indications that this might be the case. For example, the neurons, they have fiber optic-like properties in terms of refractive index. So you could actually have light propagating for several centimeters inside the neuron in the brain. And in 2016, for example, a colleague called Christophe Simon in Canada proposed, it's a conjecture based on these refractive indices, etc., that essentially, and some other arguments, that the brain uses quantum communication to do the information processing. So we don't know whether that's the case. There's no experimental evidence. There are experimental indications that it might be the case. But it's very interesting. Okay, so let's go a bit into what are the basic notions of quantum information or quantum mechanics, or in this case, states. So you all are familiar with bits of information, classical information. So zeros and one. You can write a message with zeros and one, for example. That's how classical computers work. So quantum bit or qubit is something that can be in other states than 0 and 1. So if you take this coin with the Mickey, now you can rotate it, right? And you can have it point in any direction, okay, in space. So essentially your state of this qubit, okay, can be described by the direction where this Mickey is looking at. And in fact, that's mathematically exactly or quite close to what is how a qubit is described, because it's described as a vector in something called the Bloch sphere. So this vector pointing to the top would be a 0, pointing down would be a 1, and anything in between, it's a combination of 0 and 1, a special combination called a superposition state. Okay, and so this allows you to process information in a more complex way, more generic way than these bits of information, classical bits of information. Now, so quantum communication is about communicating with very little light. Now, this is a bit a simplification. So first of all, one might be tempted to think when first thinking about quantum communication that you should carry information in every single photon. But that's not really true. In fact, in many quantum communication systems, you're not generating a single photon every time. You're in fact just taking a laser and attenuating a lot the lasers so that in each pulse you have about 1 photon on average. In fact, you can do communication with much more than 1 photon on average per pulse too. That's not a problem. So why? Because, well, a single photon doesn't mean it's quantum. In fact, everything is quantum. Your human body is a quantum state. We just don't know how to write it, right? So with any quantum states of light, even if they have a lot more photons than just one per pulse, then you could have quantum communication, secure quantum communication. But you need some quantum mechanical property of these states of light. And one of the main ones, most important ones, is that the quantum states are not or can not be orthogonal. And as soon as you have non-orthogonal states, you can have quantum communication, quantum security in communication. So let's just step a little bit back and think like, what's this idea of communicating with few particles of light? Well, you all know that if you're stuck in a mountain, you better have something to either reflect light from the sun or a lamp so that you can do this SOS signal that is here described. It's a Morse code. Let's just simplify this a bit and say I want to communicate with someone who is across this room using a lamp. Then I'll just do a very basic protocol. At each second, either I send a 0 or a 1. If I send a 0, I don't turn on the lamp. If I want to send a 1, I turn on the lamp. Well, this is a means of communicating. You can communicate a message in this way. But obviously, anyone has the intuition that this is quite redundant physically, right? Because every time you turn on the lamp, you have millions and millions of photons coming out. Why would you need millions and millions of photons to just encode 1 bit of information? In fact, you can, in principle, theoretically, encode infinite information in a single photon. In practice, of course, this is not possible. There are limitations. So if you do this, use photon per photon, then you can do 3 things, basically. And the first one is the one which is harder to understand. For this, you need to have a first lecture about quantum correlations to understand it well. But you can solve communication tasks more efficiently. So you can have a higher success rate of communicating the information that you want if you use quantum systems instead of classical systems. You can also obviously minimize physical resources because you minimize the amount of physical systems that you use to carry information and to process information. And then it guarantees physical security. How does that work? Well, a very basic example, of course, it's more complicated, but we'll come to it. A very basic example is that essentially I want to communicate with someone. So we're going to use a fiber optics cable. And we've talked beforehand, so we know what the protocol is. I'm going to send you 1 single photon per second and each of these single photons will have some information that you can decode. So we've also characterized the fiber, meaning we bought the fiber, we tested it, we know what the losses are. So I know that if I'm communicating with Bob, someone on the other side, using this fiber, then I expect, for example, that 1 photon out of 100 will not get to Bob because of the losses of the fiber, okay? So we're communicating, let's say we communicate 100 photons, and all of a sudden we notice, oh, wow, instead of 1, 10 photons disappeared. How did this happen? What are the possible explanations? Well, there are 2. Either the fiber broke, its physical properties changed, or someone came and physically manipulated the channel. So you have a mechanism of identifying an intruder. So that's what quantum communication gives you, these 3 fundamental things. Now, of course, how do you emit a photon one at a time? That's not very easy. Lamps emit a lot of photons. It's hard to capture just one of them. So there are many ways. The two most basic ways, I would say, are one of them is based on entangled states. So these pairs of particles which are correlated at a distance. So essentially you generate using a nonlinear crystal one of these pairs. So you have 2 photons coming out at the same time. Technically they don't come out at the same time, but then you correct it. And then essentially, since you know that every time you produce a pair, then if you measure one of the photons of the pair, you know that there's a photon on the other side. So that's a single photon source. Heralded, because heralded means announced. So essentially, when we detect in the heralding detector the presence of a photon, we know there's a single photon coming out of our device. Okay, and we can use that for communication. But that leads to higher security, possibly, than the version on the right. However, it's technically more challenging to implement, which in turn leads to security problems because it's more challenging to implement. So it's a complicated, it's not always simple to figure out which one should be used for security. The second one here, the other example is what I was telling you. You just have laser pulses and you attenuate them so that you have 1 photon on average per pulse. And this is much easier to do. And people have developed security proofs to prove security for quantum protocols based on this. And it works so well that most commercial quantum cryptography systems use this. So it allows for much higher rates with security. Then there's an important phenomenon or theorem, which is called the no cloning theorem. So you cannot clone a quantum state. You cannot exactly copy it. So if you try to copy a quantum state, in fact, part of the time you will just produce noise, random stuff. Okay? So this means that if an attacker tries to copy the information, he will end up with a lot of noise, which is also a mechanism to guarantee security. Now, you also need to detect single photons, obviously. So as you might be familiar, most single photon detection or low light level detection in the past has been based, and still today is based on semiconductor technologies. For example, in the visible range, we can detect at 60% detection efficiency, even a little bit more. But in the telecom with semiconductors, usually you can detect with 30% efficiency at most. And when I was doing the PhD thesis, I remember thinking, it's probably going to take more than my lifetime to be able to, for people to be able to detect photons with 100% detection efficiency. Well, I was absolutely wrong, because in the end, by the end of my PhD thesis, a company right next to the place where I was doing my PhD was starting to sell these detectors, which are these new types of detectors called superconducting nanowire single photon detectors, where you have a superconductor inside one of these cryostats, this refrigerator again, and you operate the refrigerator right below the critical temperature. And then what happens is that a photon being absorbed by the material will locally create heat and will raise the temperature above the critical temperature, will create, therefore, a small resistance that you can measure electrically. And this allows you to detect single photons in the telecom wavelength, where we could only detect with 30% efficiency. Now we can detect it with 100%, so like 98, 99. So this is amazing. You can detect every photon that arrives. Of course, then you have losses in the fibers and coupling, etc. But okay. One day you might have cameras based on this. And this is very interesting for imaging, for biological imaging and other things. Okay, so I think I should probably hurry a bit. Yes. So just to tell you a bit more about entanglement. So this is how you describe an entangled quantum state, specifically a maximally entangled state here. This means that you have 50% probability of both states being 0 or both states being 1. In fact, if you just measure on one side, then you have 50% probability of having 0 or 1. So it's completely random. On Bob's side, it's the same thing, completely random. However, if you look at the state globally, it's completely correlated. And this is independent of the distance, okay? So Einstein was using an example in his EPR paper to discuss spooky action at the distance, which actually has no spooky action at the distance. So the reason is, basically when you have these states, if you detect 0 on the left, you'll detect 0 on the right too. If you detect 1 on the left, you'll detect 1 on the right too. So is there an explanation that doesn't mean that you're instantaneously interfere or acting on the other side? There is. The information could have been originated from the source, okay? And you don't need a quantum state to describe that. You could just have like a classical system, okay? Classical variables, bits, classical bits. And at each round, the source is sending either 2 1s or 2 0s, okay? So this is a completely local classical explanation of the correlations observed here with the phi plus, with the maximum entangled state, okay? What John Bell came up with 30 years after the EPR paper, is that he found that if you try to generalize the Einstein scenario, and now you allow for multiple measurements that Alice and Bob could do on each side, then you have cases where you do not have a local explanation. So this was the discovery of quantum non-locality, or many times called Bell non-locality. And to have Bell non-locality, you have to use entanglement and adequate measurements. These correlations do not depend on the distance, and they have no classical analog. These correlations are usually, these games or Bell games are usually described by Bell inequalities. Okay, and I can tell you more if you write to me and if you want some references. Okay, so these correlations are essential to guarantee security in communication, and also to create solve communication tasks more efficiently, and also quantum computing. Bell correlations are important for quantum computing. So yeah, there was a Nobel Prize for Bell non-locality recently, and so when you read this type of news, now you know that this is not a good way to put it. It was not the spooky action at the distance that got scientists a Nobel Prize. It was showing that there is no spooky action at the distance, but there is something called non-locality, which is quite counterintuitive, but explainable, understandable. Okay, so we're getting to the quantum communication protocol part. I think I'm hitting the 30 minutes. I hope that I still have like 5 minutes. I can finish in 5. Let me know if there's any problem. So what you can do with these quantum correlations is that essentially you share these correlated states. There's other ways to do it, but you can share these correlated states. And then if you measure the statistics, then you can, if you have an error above some value, then you can detect that there's an intruder, as I mentioned before. So this is called quantum key distribution. So you generate a secret key. So the states are sent and measured, and the measurement results will be used as a secret random key between the parties, because they are fully correlated, so the bits will be the same on both sides, okay? And this quantum key distribution protocol generates a secret key, which is then later used for classical encryption as a shared secret to guarantee the encryption security. So here in QKD, you have several quantum phenomena which enable security. Is that the measurements disturb the states, the no-cloning theorem, non-orthogonality of states, and entanglement. There are a few key aspects. So you can detect an intruder. We already discussed that. You generate this secret key for classical encryption, but QKD works at limited rates. So in fiber, you can do at most 100 megabits per second, around that, 120, 110, something like this is the record in optimal conditions. But we want to have a quantum internet, and for this we need to use satellite links with optical ground stations. And in those conditions, it's super limited, because QKD can only hit 80 kilobits per second in the best possible scenario in nighttime. So during the day, it doesn't work. In free space, when you do QKD in free space between like two buildings, for example, it performs very, very badly during the day. It's very hard to do during the day because of the background noise, the photons from the sun hitting the single photon detectors, obviously. But with QKD, you can do a few experiments. So within this quantum communication infrastructure, which is being built all over Europe, there will be a quantum internet soon in Europe. We did some QKD experiments between Portugal and Spain, for example. So you can transfer timing information from an atomic clock securely, for example, this one application. But then there's other protocols, and I'd like to tell you particularly about one. So you don't need to necessarily generate a key to then be used for classical encryption. You can actually directly send a message with the quantum states, okay? And this is an example of such a protocol. There's this protocol, quantum keyless private communication, which is specifically useful for satellite to ground state, optical ground station links. It sends directly the information using quantum states. It's one way. So in QKD, you need several rounds of communication. Okay, here you don't, you just send everything. And the job here is to guarantee that even if Eve captures part of the light, then she cannot decode the message. You can have security with this under very strong noise conditions. So what does this do? This enables quantum communication under daylight, full daylight. So the phenomenon here is simply non-orthogonality of states. It's much simpler than QKD, this protocol, in terms of the phenomena that lead to security. So this is what we did in Technic. We did it an experiment in full daylight conditions. We didn't even have to cover the single photon detectors as we usually have to do. In fact, as you can see, the detectors were getting hit directly by the sun, and we could still prove quantum security. Okay, so then there's a lot of other developments happening in photonics which are useful for quantum communication, like new types of fibers, photonic integrated chips, and particularly something that I really enjoy, but today I don't have time to talk about, is optical quantum memories, which essentially is a device that stores the quantum state of light and then releases when you want. You need that to have quantum communication networks. You need that to have quantum random access memories for quantum computers. You need that for a lot of things in quantum techniques. So just wanted to mention a bit that there's this quantum internet being created. There's already a Lisbon quantum internet, which is operated by Gabinete Nacional de Segurança. And this Lisbon quantum network is going to be now connected to the Spanish quantum networks and in the future to the whole European scenario. So this is essentially what we'll be doing. So this essentially it's what the future will look like. It's quantum communication links between Lisbon and Vigo here to the north, and a satellite link with Madrid, for example. We already started this work, which finished in the end of the last year, but now we're joining the second project, the second phase, which is to connect Portugal and Spain, and we're going to install during the next 4 years 4 optical ground stations in the Iberian Peninsula, one close to Lisbon, between Lisbon and Évora, one in Madrid. These locations can still change a little bit, but one in Madrid, one in Barcelona, one in Vigo. And there will be satellite links to this quantum communication. So if you want to communicate with quantum communication during the day, you cannot use QKD, you'll have to use direct messaging type of protocols. Okay, this is just a slide about the group in Technico. We do quantum information theory and experiments, a bit focused on quantum communication, but we also do a bit of sensing and computing. And I think I already took quite a lot of time. This is the new lab that we inaugurated this year called the Quantum Information Quantum Optics Lab. Thank you, and sorry for going overboard 5 minutes.
Thank you for the presentation. So we have the time for 1 or 2 quick questions before advancing for the next presentation. Anyone? Yes, no, maybe. I think so.
Okay, Manuel, are you listening me? Yes, can you listen or not?
No.
Sorry. I don't hear super well. Sorry, what did you say?
I was just asking if you are listening.
I am listening, yes.
Okay, Emmanuel, great presentation. I just have one question about when you describe the technologies for photon detection, where do you think, trying to get more broadly, where do you think we are going and what are the challenges now? So you can already detect with a very nice quantum efficiency. But now what will be the challenges? Is to scale these technologies to multiple channels?
Yes, so that there are a few challenges that I know of, and surely there are more. So one of the things is speed of detection. There's these detectors, like the semiconductor ones, also have a dead time. So after a detection, you have a period of time the detector is not working. But here, the dead time is much, much shorter. I think you can have down to 10 nanoseconds, and they're still improving that. It's much better than the semiconductors. Also, you can have less dark counts. So when there's no light coming in, you also have some noise. You can have less dark counts, and that has to do with the physics of superconductors. I'm not specialized in it, but I can point you to references. In fact, I have a colleague who is probably, if not number one, one of the 5 top experts in this area. So those are just improving the performance of single photon detection, okay? But then there are really interesting directions. So one of them is photon number resolving detection. So instead of just saying I have at least one photon hitting the detector or nothing. Now I want to say in this pulse, I had exactly 4,323 photons. You see? So that is really revolutionary in the sense that we didn't have photon number resolution resolved detectors until very recently. With these superconducting ones, now you have a model being sold which can count up to 8 photons, but the fidelity, the probability of successfully detecting goes down, okay, with the number of photons. So you don't get 100% efficiency with the 8 photons, you get less, but it works. You can count. Recently, there was a work by Christine Silverhorn that showed with a bunch of these detectors, so they used a lot and they essentially multiplex the detection to be able to count even more photons, and they could count precisely up to 9,000 photons, which is absolutely amazing. And this is the kind of stuff that will help us understand if quantum mechanics applies to all scales, to any number of particles, because we don't know. And that might be a good way of finding a new theory of physics. And finally, doing this in free space. So, yeah, sorry, just one thing. You can also reduce the dead time, basically remove any dead time by having several of these single photon detectors on top of each other. So that when one detects, there are n-1 other ones that are ready to detect, you see? So they have this now, it's called parallel SNSPD. You also have multi-pixel SNSPD, which allow you to do that, count much faster, but also count the number of particles. And the final direction is, this is all in the cryostat. You need a fiber, you need to send the light there, and you have a lot of loss. Can you do this in free space? Can you have a camera which does this? And that for imaging would be amazing, but there are a lot of challenges with that. This is pure research, that part.
Okay, thank you. I mean, if I have one more question, I mean, it's to provoke you. People keep talking about quantum communications, and when you do optical classical communications, we typically utilize infrared. And in quantum communication, we use visible light due to the efficiency of the detectors. Where do you think the progress should head? Is to increase the quantum efficiency in this stage? Because I mean, in the infrared, you'll be plagued with thermal noise, and I mean, you cannot increase the. Of course, you can kind of get some continuous variable scheme, but to communicate with single photons, where do you think we should head? Towards increasing the performance of the detectors, or to force visible light compatibility with the infrared classical networks that we have?
I think both directions are interesting. There's people trying to convert light from one wavelength to others at the quantum level efficiently. This is good because you might want to have telecom wavelength for light propagating over fibers, but then if you want to store it, usually the transitions in materials at telecom wavelength are quite rare. So usually you want light more at visible wavelengths. So then you can have very good reasons and use cases to convert frequencies of light. But also improving the performance of the detector is very important. These detectors now just boosted the efficiency of what we can do in single photon detection at telecom wavelength to essentially perfect efficiency, unit efficiency. It's like 100%, 98, 99. So then the other challenges to be solved now is this dead time, make it even faster, being able to count photons, things like this, at telecom wavelength, but also at visible wavelength. In fact, for free space quantum communications, you might want to use wavelengths around 850 nanometers, okay? But then if you do that and you send light from a satellite to an optical ground station, the telecommunication networks are all working in 1550 nanometers, so you need to convert that, so you have losses. So there's both possibilities. You can either have everything working with telecom, or you can have parts working with infrared, more to the visible range, versus telecom. And telecom. So you could combine both. And there's various solutions. I guess it will depend on the use case or specific application you're thinking about. Yes, and then there's also visible light communication. That's more for IoT stuff. But there's no. I've seen a few ideas of trying to do quantum visible light communication, but I don't know much about it, and it seems that there's not much about it yet. I hope this answers the question. Maybe I didn't answer everything.
Yeah. Thank you.
Okay.
Thank you. So, let's thank the for the presentation.
Thank you very much.
Thank you. So, our next speaker. So our next speaker is Bruno Romero, which is a researcher and a principal investigator at International Nanotechnology Laboratory, which is ENL. So he holds a PhD from the University of Algarve and already did some research work in the University of Ottawa and Eindhoven. And he works in a lot of disciplines in the physics, optoelectronics, and photonics, and neuromorphic computing. And so today we want to talk about bio-inspired nanophotonic sensing and computing. So thank you, Bruno.
Thank you. Thank you, Tiago. Thank you very much for the kind introduction. I would like to thank SPI student chapter for the invitation. Yeah, it's a pleasure to be here. Yes, I will be talking about bio-inspired nanophotonic sensing and computing, one topic we are working at the International Iberian Nanotechnology Lab. I was told to make just short introduction about our research institute in Braga. So INL is an intergovernmental organization. So essentially, we have two member states, Portugal and Spain, and we started operating about 15 years ago when the building was finished. And it was an investment to essentially place Peninsula Iberia in the forefront of nanotechnology. And our mission is to excel in nanoscale research for the benefit of the society. And essentially, the vision is to lead in nanotechnology and fostering excellence and global recognition, and also make meaningful contributions to shape the future. Just a few numbers about our organization. Currently, we have more than 500 personnel, about researchers and engineers around 100 persons, and we receive graduates, students, PhD and master students from around, so locally from the University of Minho, University of Porto. Since we don't all degree, we collaborate with these universities, and actually our students work at INL as member of Personnel Associates. So if you are interested in any projects, you can reach out to us, and also with your supervisors or your professors to see opportunities for us to collaborate. We have 3 core facilities at INL, which allow us to make very interesting research in different areas. One on electron microscopy facility, another one on micro nanofabrication. So we have a very large clean room where we can fabricate in large wafer scale, and we work also with industry. And we also have a large facility in nanophotonics and bioimaging. And essentially, we work in 3 grand thematic areas with about 20 research and engineering groups. The areas are information and communication technologies, energy, environment, and life sciences. And today I'll be focusing more on the ICT, but a bit connected with life sciences. We have different groups at INL working from graphene, NEMS, MEMS, Fintronics, nanophotonics, system integration, autonomous sensors, beyond CMOS, quantum science and technology. Specifically, I work on the quantum bio and nanophotonics group in NIDA group. We also have Jan Miller today here. We work in different topics, and three of the key topics include nanophotonics, active devices, nano LEDs, waveguides, 3D waveguides. We have a big portfolio of devices. We work in quantum science and technology. Specifically, Ananida works in the NV Center, Diamond Photonics platform, and we have now big investments within the pilot lines in Europe to advance Diamond Photonics platform. So you feel free to reach out to us. New paradigms for computing is also a topic I'll be talking today more in detail, specifically on the neuromorphic brain-inspired computing using a photonics approach. And this comes to the talk today. So I'll be talking about insects a lot, although this is not my field, and I will make the connection to photonics in this talk. So insects are a unique example of natural intelligence because they can sense the environment, very complex environment, and look for food or navigate in very complex environments with a very small brain. And they do this very efficiently. Artificial intelligence is the intelligence we invented, humans invented, that works quite different from this type of intelligence. So our aim is to be inspired of some of the process we see in nature, try to emulate and find applications we could use. So one of the motivations for this relates with the computing power demands here shown in the last 4 decades. And you can see three trends in the demand for computing. The first one that came from since the invention of the transistor and the digital computer. So the Moore's law that is doubling every 24 months. So this is essentially related with the evolution of the computer. And now we scale transistors down to smaller and smaller scales. It's the blue curve. But more recently, since about 2010, with this new wave of neural networks that actually started back in the 60s and then it was dying and then regained attention. And finally, in 2010, also because of computers started to be very powerful, we could build neural networks and compute neural networks in computers. Since then, see in green, we have this doubling every 3.4 months, the computing power. And more recently, also with ChatGPT and all these processors, we have doubling every 2 months. So the artificial intelligence has been demanding more and more computing power. And this is known, and everybody talks about it. But what is the bottleneck? So this is also the graphic representing some of computers along the years with the clock frequency that more or less stopped growing for some years now. But what you can see is the power density of these computers as compared with the human brain. Human brain, in terms of clock frequency, we don't really have a clock, but our neurons operate with action potentials that are on the Hertz scale. So it's very slow, and it's also analog. But digital computers are quite different platform, but they consume a lot of power. So we have 4 to 5 orders of magnitude computing power difference. Our brains compute, let's say, with about 20 watts only. So it's quite efficient. So the main reason between these two very different architectures, so artificial and natural intelligence, is based on the building block of the architecture. So as you know, central processing units, so they operate between shuffling data between the memory and the CPU until you get the result outcome. And this shuffling of data dissipates a lot of heat, and essentially it's electrical information that is computed. So there's a bottleneck to make it more efficient because of this shuffling. Biology, so the natural intelligence use neuron cells. neuron cells are highly nonlinear biological systems. And you can find this type of biological cells in every type of brain, from insects to human brain and so on. So it starts with the nervous system. So the first organisms, they were, communicating with this type of spiking signal, and then evolved to more networks as a kind of central processing brain. So neurons are excitable because essentially the way they communicate, they have these dendrites that receive spikes or action potentials from other neurons in a 3D network. They sum this in the neuron, and after a certain threshold, it activates an action potential, which is a nonlinear pulse with always the same shape and more or less same amplitude. And it only fires a second spike or action potential after a certain refractory time. So this is the basic principle of neurons. And actually, there are different types of neurons with different types of nonlinear signaling. We have neurons close to sensors in the eyes, in our ears, and they do pre-processing before going to the brain. So it's a very complex system. So the human brain is indeed huge in terms of billions of neurons that we have and trillions of synapses. So far, we were not able to map entirely our brain. So we did in the last 20 years quite remarkable advances, but we are still far for understanding the full complexity of the brain, the human brain. The insect brain is much smaller. So the brain volume is about 0.08 millimeter cubic, and it has about 10,000 neurons and 10 million synapses. So actually, brains of insects are very interesting because we can study them entirely. And in 2024, we got the very first full map of an entire animal brain. So this is the first time we were able to map a brain as complex. In this case of the adult fruit fly, which is still a very small insect. So there are insects much larger. So this is a Flywire project, a consortium of dozens of research labs across the world. Essentially, they took, they did electron microscopy of different images of sliced images of this brain, and they were able to essentially make what they call the connectome. So all the connections and identify all the neurons and circuits and subcircuits of this brain, and actually can go online and see this full map and go like in Google. You do in Google Maps, you can also go here and see all the connections. And essentially, this is the size of the number of neurons and synapses you have in the adult fly. So the reason why we are interested in this type of brains, especially insects, is that 70% of the insect's brain is dedicated to processing vision. So vision is a big part of also what humans do, and this has enormous potential to different wide applications, like in drones and processing video type of information and so on. That's why we are so interested on this type of brains. And also there's a unique capability of insects, and this happens with all insects, from bees to ants. They have a natural autonomous navigation system. So they have an internal GPS without the need to be connected to the internet, okay? So the way it works is, so imagine a bee that goes in a foraging trip to look for food, and it will go random, and it can go in a completely different environment or new environment, and it goes around, and what it does is use sensory clues, like vision, the optic flow, smell, and other clues, to essentially do this path and map in real time points of interest and obstacles. So using this, it builds internally in the brain a home vector, a path integration. So why it's flying is also learning. And this allows the insect, when it finishes the trip, it comes almost directly straight to the nest or the hive in this case. So, and it does this very efficiently. So it navigates essentially using the environment, collecting information, memorizing, and then returning because it has internally a kind of compass. A crucial point about this navigation system is that insects are sensitive to polarization of light. So as you may know, light on Earth is polarized, so the light we see from the sun is polarized and depends on the sun elevation. And actually, the eyes of bees are essentially optimized to exactly be sensitive to that polarization. So the way it works, so this is an example of the eye, and one example of a cell in the very complex eye, where you can see some photoreceptor cells, so they are sensitive to light. And they have this, what they call microvilli, which are these structures that are oriented in two directions, which is used to detect polarization. And then this also is also connected to neurons that essentially pre-process this information before sending to the central brain of the insect that processes the entire information from the eye. So the way it works is that light is received in the eye. So there is some processing where this light is converted in this spiking signaling, this train of spikes. And then this information, it goes to the center of the brain of the insect, which is called the central complex, that contains a network, a circuit, which is called the central complex, with three ring layers. The first one is where no information from the eye is received, and it essentially computes the direction. Then the second layer of interconnected neurons memorize this direction, and the last layer essentially makes the steering, so makes the decision if the insect turns left, right, and so on. So what I'll be talking today is our efforts to try to build like the first kind of layers of receiving light, transform this in spiking, and eventually being able to pre-process this information before going to the brain. This is a project we are involved called Insect NeuroNano. It's a European consortium led by University of Lund in Sweden. And essentially it's to build an insect brain inspired architecture based on nanophotonic components. So what we are aiming specifically at INL is to try to build this first layered structure in the eye of the insect. So first photoreceptor neurons, neurons that can also be sensitive to polarization of light, and then eventually also process this information to have in a compact chip some of the features we can also find in insects. So the platform we use is based on nanostructures, nanopillar arrays with different shapes to be able to be sensitive to light and also be able to trigger this type of spiking activation signals. So in the next few slides, I will briefly discuss how we implement this. It will be a bit more in depth of what we actually do in our labs. So if you have any questions, then we can discuss. So the platform that you can see, it's a nanopillar platform. The materials we use are gallium arsenide substrates. So this is a very mature semiconductor platform. Actually, it's used on your phones for the facial recognition application, where you have these arrays of lasers. They are built of the same material we use here. The difference is that we nanostructure the material to these very small pillars below 1 micrometer in size. And we engineer the material with different stack layers that we can grow using advanced methods like molecular beam epitaxy, where you can grow different layers of different semiconductor materials to make essentially though the highly doped layers for the electrical contacts of our photoreceiver detectors, and also to engineer some properties I will explain later, like a nonlinearity that allows you to have the spiking kind of behavior. So we use this architecture, in this case, as a photoreceptor, as polarization sensitivity, and as a spiking. So the first goal we are working on includes how to operate these as photoreceptors. So this is a semiconductor material, so this particular one is very sensitive to near infrared because of the band gap of the material, so around 850. And it's not so sensitive to visible light, but actually insects, they are very sensitive to the blue or close to UV light. So we wanted to have our pillar architecture more sensitive to blue light. So what we did is we nanostructured the material with different pitch and different sizes and tried to improve the absorption of light. So if we engineer well this pitch and size of the pillars, we can actually enhance the absorption. So essentially reduce the reflection of light that is being transmitted and enhance some of resonances that are more sensitive in the blue. So that's what we've been exploring with different type of shapes, including circular nanopillars and also flower shapes. Interestingly, we still have to do some measurement on this, but it seems it's also very interesting for absorption in the blue, this type of architecture. So the second challenge was how can we make these pillars sensitive to polarization? So the idea actually is not so difficult, is essentially to shape the pillars in a more anisotropic way so that we have a kind of elliptical shape with different directions. So we build arrays in different directions. Here an example in 4 different directions. So X, Y, like 45 degrees, 90 degrees, and so on. And because of the anisotropy of the system, essentially, if you receive linear polarized light, you'll get more absorption in one of the preferred angles, right? So with that, if you then make connections, electrical connections for each array, and we collect the photocurrent for light that is in one transverse orientation, we get more absorption, we get more photocurrent, and with that, we have enhancement of photo detection in one of the arrays, and with this we can compute or try to compute be sensitive to polarization. And lastly, this is a bit more challenging to explain because it's a bit more complex architecture. How do we engineer the spiking of the behavior in this semiconductor material? So what we do essentially is we engineer the material to have in the layers this structure that we call the double barrier and the quantum well. And because the size of these barriers is about 2 nanometers, the well is 6 nanometers. So this is the size of essentially the electron waves. So what happens is that you have specific resonances or transmission that is filtered in this structure. So carriers that are essentially flowing in this device will be filtered or not by this structure. The way it works is like this. So you have this resonance level, and you apply a voltage across the top and bottom contact so that you can have flow of carriers. No, electron and holes start to flow. And in one side of the contacts, you have this reservoir of carriers that are starting to be transmitted. And essentially, you have, when you apply the voltage, you bend this structure and you have a maximum probability of an electron to tunnel and when it's aligned with the resonance. So this is a tunneling effect, a quantum tunneling phenomenon. And this resonance allows to have the control of the current and voltage across the device. So when you apply voltage initially, the current increases, it follows the Ohm's law, so you have positive resistance. So this happens in any optoelectronic device or electronic device. But at some point, we call the peak voltage when this resonance state is not aligned. So when it goes below the Fermi level. So you get a reduction of current. So current decreases. And then eventually electrons can flow over the barriers and you get current up again. So this is highly nonlinear. So you have current going up, current going down, and current going up again. So we call this a negative resistance. So a negative resistance in electronics is equivalent to having a system with gain. So we use this property exactly to trigger this spiking behavior. And actually, the model of this system is similar to neurons. Like for those familiar, the Fitsug-Nagumo neuron model is similar to our neurons. Essentially, the operation for triggering spikes is that we operate the system very close to this negative resistance region. If it's perturbed by a small signal, if it goes above a certain threshold, it triggers a large spike or voltage peak, and then goes to the red state and waits for the next trigger to spike again. So this is the principle of operating this as a loop. So we tested this in the lab, and we tested with optical incoming signals. So actually what we did here is a bit different. We placed the device inside the negative region, and because it has gain and it has associated the LC circuit, it starts to oscillate at a given frequency. So it builds oscillations, and what we do is that we perturb the system with an optical input, a modulated optical input signal. And when we increase upon a certain threshold, it starts to trigger these trains of spikes, so these bursts of spikes. Essentially, we can emulate these very different type of nonlinearities, like bursting, spiking, oscillations. So it's a very rich dynamic system. So essentially what we do, we can optically encode information from the optical domain to this spiking train of signals as oscillations, and we can explore this as the first pre-processing layer of receiving light, eventually receiving polarized light, and depending on the light received, we can trigger or not the spiking behavior. So with that, this is current our status of work, and we are starting to build this in kind of array systems to receive more and more number of signals to be able to have more complex systems. So with that, I wanted to thank the team, especially João Azevedo, that is our student behind of most of this work related with the fabrication of the pillars and testing in our lab. And before going, just sorry about the advertising, but we also have our International Day of Light event on Monday afternoon. So you feel free if you want to visit us, not only students, but your families. We will dedicate this year to the dark side of the moon, inspired by the flyby of Artemis, and also we have the eclipse this year. So we have a wide range of activities there. If you can feel free to reach out to us if you want to join. So thank you very much.
We have now the time for some questions. Yes, Professor.
Okay, well, let me shift to Portuguese. I think I take this back of the same. O primeiro ponto é importante salientar o aspecto importante de estar controlado de alguma forma. Ou seja, olhar a natureza para tentarmos perceber, em vez de ir lá à força bruta, não. O que acontece, tentamos perceber o que a natureza faz. Mas a minha pergunta, quando representaste o esquema de navegação da abelha ou da mosca, Depois me queria pensar uma coisa que é para mim uma grande interpretação. Há muitos, mas há uma que nos fascina particularmente. Quem conhece os sistemas GPS ou os sistemas, digamos, nossos de navegação, tem o hardware, são os satélites, os receptores, e depois o software é brutal. Quando eu olho o sistema de navegação da frente, que é acessível à polarização dessas coisas, aquelas camadas todas, eu olho aqui e parece-me o hardware. A pergunta que eu coloco, e o software? E essa solução é boa? É pensado sequer. Eu acho que essa é tão crucial. Obviamente estão a replicar, digamos, todas essas estruturas de hardware que aqui estão, e vão conseguir certamente. Mas depois vão ter que pôr inteligência para guardar aquilo tudo. E uma coisa que às vezes me impressiona é que no âmbito das ciências biológicas, por vezes esquecemos um aspecto fundamental que faz com que isto é muito fantástico, mas para funcionar tem uma qualidade de software brutal. Queria saber que repartição de sobre isso.
Sim. Obrigado pela pergunta. Na realidade, eu não trabalho na biologia e os nossos colegas neurobiologistas é que trabalham com os insetos. E na realidade eles testam isto em software. Eles têm modelos e têm um software que representa realmente os modelos e tentam verificar se realmente os modelos representam os testes feitos. Eles fazem um mapeamento dos circuitos e tentam arranjar os modelos mais próximos possíveis. Claro que não é fácil em software representar todo o modelo do inseto, mas em princípio seria possível. Realmente a vantagem do hardware é permitir substituir o software em algumas das tarefas. Claro que o software, na parte humana, na parte do desenvolvimento humano, o software serve para controlar o hardware. Portanto, os algoritmos que vão ser necessários para controlar este tipo de sistemas, de facto, eles existem, mas ainda não estão suficientemente testados para o caso dos spikes. Eles existem, mas no caso dos cérebros naturais, dos insetos, como a nanolinearidade é bastante elevada, não é muito fácil ter software compatível. Por isso, eu acho que, resumindo, o grande próximo passo é tentar arranjar os algoritmos certos que, de certa forma, consigam trabalhar com este tipo de hardware muito diferente do hardware convencional, que é digital. Essencialmente.
Recall. So going back to the last graph that you showed, can you explain it better? Because those pulses, so you plug those pulses, the last one. Yeah, that one. So you apply those pulses in that regions, and in between it goes back to the previous state.
Yeah. So essentially, what we do is we are forcing the system going from the oscillating state to the rest state. So what we do is to perturb the system with sufficient, in this case, optical energy that is transformed in a photocurrent to force the system to go to the rest state, and it will stay silent. And then when the perturbation goes again away, it continues oscillating. So it's the perturbation that forces. So in mathematics, when we have perturbations, we have a limit cycle, so there is switching. And the system kind of makes these transitions from positive to negative. And when it's in the rest state, essentially, the perturbation doesn't allow to make this large excursion of the entire system.
Okay. And in the future, do you believe we can utilize those pulses to emit lights? So
yes.
Like with an LED?
I didn't mention, but this is also one of the ideas we are exploring because our devices also emit light, is that we can have modulated light in the output. So you have not only electrical spikes, but also optical spikes that continue. So the idea is exactly that we could encode the information in the light and also do it optically and not only electrically. Yeah.
So let's
So before going to lunch, we'll have a small moment which will be presented by Dr. Enio Dias. That's, I will give you the floor.
Boa tarde, eu vou falar em português, que é mais simples, e esqueçam tudo isto que estiveram a ouvir, porque está na hora do almoço. E quero, antes de mais, agradecer ao Chapter o convite que me fez. Queremos fazer uma pequena, o Chapter quer fazer e pediu-me, não sabem o que estavam a meter, e muito menos eu, uma pequena homenagem a uma pessoa, já vão ver quem é. Eu tenho uma pequena apresentação, muito breve, com alguns disclaimers iniciais. A terceira, olha, foi, quer dizer, depois das outras que eu tive números negativos, percebes? Comecei na menos 50. Isto faz andar para a frente, é? Aqui?
Temos que apanhar.
Sim, ok. Não, eu fiquei assustado com como é que se está a dizer, a cerimonialidade desta pequena apresentação, porque eu julguei que era uma simples brincadeira, e é assim que eu vou tomar, portanto, peço desculpa para quem sai assim de um tom tão sério para um tom não leviano, mas mais leve. Vou falar sobre uma coisa muito importante, que é o Mistério do Algarismo 4, sabendo da presença da Madonna no festival em Lisboa, onde este está a cabala, e vai ser muito importante para daqui a pouco. Não usei nada da AI, mas os problemas todos da AI estão aqui todos, mas com uma grande vantagem que é tudo com inteligência natural, ou até estupidez, portanto, quer dizer, eu sou inimputável neste período de tempo, habitualmente. Portanto, por favor, quem aqui aparecer, não me corrija, porque não adianta. Da internet diz que o número 4 está relacionado, e o 44, lá está, 4, 44, 444. O 44 está relacionado com a materialização, e já estou a dar o spoiler, mas 4 também, o 44, como aparece duas vezes, relacionado com 8, portanto, é a pessoa que soluciona qualquer problema. Tudo aquilo que ela pensa pode tornar-se realidade. Até, nomeadamente, ecrãs avisadores de autoestrada, que são uma coisa muito difícil de realizar. Tudo isto começa com o 4, quando a pessoa de quem estamos a falar, e é o homem, começou a pensar na questão da barba. Era muito comum estes produtos, e como estão a ver, 444. Portanto, ele achou 4 sim, 44 está bem, 444 é demais. Portanto, para quem não sabe, isto é uma marca de produtos para a barba que ainda existe, só se compra pela internet, mas na altura comprava-se em qualquer mercearia. Especialmente aqueles lápis hemostáticos estavam em quase todos os barbeiros. Para mais, vamos começar por tentar identificar a pessoa, para quem ainda não conseguiu. A pessoa não está nesta fotografia. Portanto, aqui estão outras pessoas notáveis. Estão professores aqui desta casa, pessoas que já se reformaram, docentes da UTAD, docentes da Fernando Pessoa, do IPP, da FEUP, empresários, pessoas de férias, como aquela última ali do lado esquerdo, que não está cá, diz que é sabática, mas a gente sabe bem como é que é isso. Mas nesta altura a pessoa já trabalhava nisto. Aliás, a pessoa com quem estamos a falar foi o primeiro investigador em Portugal da área da optoeletrónica, fotónica e etc. Muito menos está aqui, embora já existisse aqui. Eu gostava de legendar a fotografia. Há pessoas que é imediato, mas a segunda, a partir do lado direito, da parte de baixo, é mais difícil. Mas está aqui na sala e, portanto, que se acuse se quiser. São pessoas do início do trabalho da fotónica, mas a pessoa de quem estamos a falar, novamente, não está aqui ainda. Portanto, acho que isto, por exclusão, já conseguem lá chegar.
Pode ser.
Posso dizer o quê?
A pessoa do lado esquerdo, do lado esquerdo todo, direito do lado direito,
Professor Leite.
Não, eu disse esquerdo da fotografia.
E essa pessoa sou eu.
Estava a referir-me àquela pessoa.
Do lado esquerdo.
Não, do lado esquerdo todo, acho que, enfim, o professor Pereira Leite está extraordinariamente bem conservado, porque lá está.
Bem composto então.
Não, está. Estamos a falar, isto acho que é uma fotografia de 88 ou assim, não é? Nos Leões, onde é agora a reitoria. Está ali também um professor.
80 e pouco.
Pois. Está ali também um professor da Universidade de Aveiro, que há uns anos foi acusado de bullying. Portanto, temos aqui uma... É verdade. Eu não vou indicar por razões óbvias, não é? Mas também está ali. Está um professor da Faculdade de Engenharia e estão outras pessoas. Eu não me lembro dos nomes, mas lembro-me das alcunhas que nós, alunos 3 anos mais novos, tínhamos mais ou menos para todos eles. Não vou dizer, nem imagino. A pessoa que estamos a falar é uma pessoa da física, mas que se dedica também à sociologia. Quem não conhece, há um livro do professor António Barreto, que foi político e sociólogo, etc. Tem vários livros de fotografia. E tem um livro que é sobre o Portugal dos anos 60, 70, 80. Porque já nessas décadas a pessoa que estamos a falar era viva. E, portanto, o António Barreto, o professor António Barreto, decidiu fotografar os portugueses em Portugal. A pessoa de quem estamos a falar, em breve vai lançar um livro sobre os portugueses no estrangeiro na mesma época. Onde se mostra o amor pátrio, porque não é um produto comprado num supermercado qualquer, é Ajax. Portanto, e isto é um parque de estacionamento, a matrícula já não existe, portanto, isto faz parte. É uma fotografia, lá está, agora estamos a entrar nas fotografias tiradas pela pessoa de quem estamos a falar. Portanto, aqui já conseguem ver um bocadinho. Eu suponho que isto é um parque de estacionamento e, portanto, a pessoa que não diga nada, porque senão acusa-se já, algures entre Portugal e a Itália, das primeiras delegações de fotónicos ao estrangeiro. Isto também faz parte do Portugal desses anos, porque não havia aulas de cidadania, inclusão e diversidade. E, portanto, para as pessoas verem coisas tão simples como estas, tinham que ir ao estrangeiro. E, portanto, está aqui notado realmente a precisão com que, portanto, era possível obter formação em áreas da sociologia, não é? Daí o interesse da sociologia da pessoa de quem estou a falar. A curiosidade não é pelas peças, a curiosidade é, que está ali espelhada, como é que a fotónica, a optoeletrónica, falava-se mais assim, vai conseguir ser aplicada no vestuário, não é? E daí nasceu aquele centro tecnológico que existe em Famalicão, que trabalha nestas coisas. Foi tudo desta altura. Portanto, esta é uma fotografia em que a pessoa está, a pessoa tirou, e depois tem aqui uma pequena conjunto de características da pessoa que podem ajudar a descobrir. Portanto, se quiserem saber o que é que há, o que é o almoço na Casa Expresso, em qualquer dia, a pessoa sabe, diz, há mais de 40 anos que sabe. Quando esteve na Universidade do Arizona, sofreu a praxe habitual, que é deixar as pessoas tocar nas coisas metálicas e apanhar um esticãozinho. Portanto, foi praxado lá também. Um dia, num projeto nos anos 90, um projeto em Israel, antes de tudo, o voo foi acompanhado por um espião da Mossad que sabia quase tanto de lasers como ele. Portanto, isto não é... E ele, pronto, o que é que ele ia fazer, etc. Foi uma conversa muito interessante, pelo que vi. E não usa gravata, mas bolo tie. Já aparece nesta fotografia, que suponho que 84, lá está como a professora Praletes estava a dizer, há ali pessoas que se conseguem identificar. Posso dizer que do lado direito, e acho que também é uma honra para nós dizermos que está ali um pintor amador, meio marginal da Rua das Flores, que distinto doutorado em Engenharia Mecânica e uma pessoa casa a casa, uma pessoa que acho que continua a ser aquilo que o seu nome diz, que é feliz. A ver, vamos. Portanto, já ali está. Alguém tem alguma pista? Não pode dizer, só estou a perguntar se tem pista. Pronto, como não tem, eu vou dizer que está nesta fotografia. E, portanto, e é uma pessoa que está a fazer 44 anos de aturar alunos e vice-versa também. Portanto, isto é direcional. Daí a importância do 4, não é? O aspecto divino de conseguir fazer tudo o que quer. O 444 não, por causa da barba, porque não precisa. E os 44 anos que tem estado nesta Santa Casa a trabalhar com toda a gente. 20 anos antes, ou melhor, 20 anos depois disto, não, nesta ocasião, 20 anos antes dos morangos com açúcar, ele decidiu mandar isto para o casting. Mas como ainda faltava 20 anos para... Não foi selecionado. Não foi selecionado. Uma coisa grave, porque podíamos hoje ter aqui este colega, em vez de estarmos a falar dos 44 anos, estamos a falar dos Oscars e dos BAFTAs e das coisas todas, que eu, de certeza, como quase divino que é, por causa do número 4, teria realizado. Reparem o duplo perigo, não é? Há ali duas coisas de danger. Portanto, há aqui toda uma postura, de herói. Está tudo cinema mesmo. Bem, terminando a brincadeira, Manuel Joaquim, para mim é um grande privilégio. Em meu nome, e acho que em nome de todas as pessoas que estão aqui na sala, anteriores alunos, atuais alunos, aqueles que futuramente já não serão teus alunos, que se calhar também estão cá, a seguir colegas, docentes e investigadores, professores, enfim, e toda a gente que contactou com ele. E em meu nome pessoal queria dizer-te que foi um grande prazer ter-te como professor. Aprendi muito, ensinaste-me mais fora das aulas do que nas aulas, porque acho que é aí que vale a pena, porque nas aulas isso está tudo nos livros, e é realmente, sei lá, muito para mim emocionante poder estar aqui, e não sabia que isto estava para tão breve. Por isso, mais 44, e cá contamos contigo. Há ali um... Faltava esta frase.
Devo dizer que a pessoa que ali está, o amigo Manuel de Sousa, também colega de curso, foi longe mais brilhante do Luís. Como se mostrou ao longo dos anos todos, quando precisamos de ver alguma coisa difícil de física, nós para a cabeça. É uma pessoa que num grupo é crucial, porque quando é preciso alguma visão diferente, vai falar com ele. E no grupo de investigação que veio este da portal eletrónica, assim por diante, não, foi descoberto. Eu não sabia que isto ia acontecer.
Nem eu.
Eu tinha, na altura certa, obviamente, digamos, ainda estava escrito, não estava escrito. Mas é isso que eu digo. Foi para mim um privilégio, um orgulho e uma sorte ter como colega de curso e como amigo.
Não, é que além de mais, ele sabe de biologia, ele sabe tudo, de botânica. Quer dizer, é daquelas pessoas das quais a gente, caladinho, tem inveja, não é? E quando for grande quer ser como ele. Não sei se o chefe tem mais alguma coisa a fazer com referência a isso. Joana.
Obrigada.
Nada.
Se quiserem lá, para entrar no falando.
Eu queria primeiro dizer que ontem veio aqui a última hora e esse grupo está. Espero que daqui por 44 anos também andem por aí.
Bem, em nome do Chapa, mas também de toda a gente do carro, temos uma pequena prenda.
Até sabem que eu gosto de canivetes. Não disse alguém que isto é ilegal, mas portanto, ninguém vai ver que isto é uma coisa ilegal comigo. Ora bem, eu quando me mandaste um e-mail a dizer que era importante estar aqui assim, eu fiquei com algumas dúvidas. Mas não preparei nada. Aliás, estas semanas têm sido um bocado complicadas, principalmente porque para a semana vou andar a esfregar aqueles pobres coitados ali com as avaliações de laboratório, que alguns que estão por aqui ainda se lembram do que é que soaram nos laboratórios, mas não soaram tanto como aqui o professor Pereira Leite costumava fazer. Não, estou a brincar consigo. Mas andámos durante os anos também a colaborar. O José Luís e o Pereira Leite renovámos os laboratórios de segundo ano em 95. Foi uma tarefa hercúlea preparar todas aquelas experiências em pouquíssimo tempo e remodelar o ensino laboratorial. Portanto, eu sempre tive um gosto pelas aulas de laboratório, porque acho que é onde uma pessoa percebe muitas das dificuldades. A parte teórica é sempre muito, costuma-se dizer, simplificada. É tudo muito bonito. Mas quando uma pessoa começa a mexer, acontece a bateria começar a respirar, o aquecimento aqui, tem que corrigir a parte dos sensores de fibras ópticas. É que se a gente puser lá um bocadinho de potência, eu cheguei a pegar fogo em cima de uma mesa óptica porque partiu uma fibra e estava um papel ao lado. Com alguns watts de potência na fibra, pega fogo. Mas pronto, não convém de fazer isso dentro de um pipeline de gás, mas pronto, ou num hidrogênio compactado. Pronto. Mas no laboratório a gente tem mais coisas que nos aparecem de lado e que nos obriga a estar sempre a pensar o que é que pode acontecer, o que é que está ao lado, e que nos obriga sempre a ter uma vida sempre. Está certo, está errado, há aqui alguma coisa que eu não estou a perceber, e isso é muito importante para nós conseguirmos se ingrar aqui na vida. Por outro lado, eu posso dizer que tive 44 anos numa vida interessante. Muito stress, muitas vezes, muitas complicações, mas não voltava atrás. Não voltava. Pronto. Obrigado.
Okay, so thank you everyone for coming. In the afternoon, we will have our photonics sprint for the students to compete against each other next door. So to the students, I would ask them to meet us around maybe 2 because we are a bit late. So thank you all and sorry for the delays. And if you could all join us up here for a group photo, please.
Não tenham vergonha. É que preciso. Olha, vamos ter de nos baixar aqui. Ficamos aqui embaixo. Não tenho nível, não tenho nível. Mas vocês são todos formados, eu estou aqui a Posso ficar aí? Posso? Não deixa. Deixa bem.
Dá para sentar?
Claro. Senta aí.
Se não me engano.
O número na tropa foi 44.
Ia começar.
Mas isto não quer dizer estarmos a falar de
Rápido. Mais uma, mais uma.
Este é preciso.
Já fiz um bocadinho melhor.
Acho que é melhor desligarem a luz branca.
É melhor desligar.
Eu só ligo.
Sim, sim, sim.
Agora falta-me.
Thank you.